The Big Bang occurred in just a split second, and the entire universe was born in the blink of an eye. Have you ever wondered how the universe, with its billions of stars, planets, and even us, came into existence? Everything we know, from the radiant stars in the sky to the atoms within our bodies, began in one extraordinary moment. So many incredible events took place that it would truly blow your mind. Let's travel back to the first second of the universe. In this instant, there was nothing. No space, no time, no matter, not even energy. Suddenly, from absolute nothingness, a fireball smaller than an atom emerged, with a temperature tens of trillions of times hotter than the core of the sun. From this tiny point, everything that would become the universe exploded, expanding from a point millions of times smaller than a pinhead. In that first second, it was as though a blueprint for the entire cosmos was written. The secrets of creation, the mysteries of everything, are hidden in that brief moment. And today, with advanced technology, we are closer than ever to uncovering what happened in the most pivotal second of history. When astronomer Edwin Hubble made a breakthrough in 1929 by discovering that galaxies are moving away from us, he opened up a whole new chapter for science. This led to the concept we now call the Big Bang, the idea that everything we see in the universe once originated from a single point. Hubble observed that light from distant galaxies became redder the further away they were, a phenomenon known as redshift. This proved that galaxies are moving apart and that the universe is expanding. Scientists now believe that within the first second after the Big Bang, the foundation of the entire universe was created. But to fully understand what happened, we need a unique unit of time, called Planck time. In a moment as short as 10 to the negative 43rd power seconds, that's a decimal point followed by 42 zeros and a 1, the initial fireball gave rise to the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. Without these forces, there would be no stars, no planets, and no life. And from that split-second spark, the first building blocks of the universe came to be. We live in a universe where every atom, every planet, is a remnant of that first instant. The journey of exploring the universe is a journey of understanding our origins. To understand the cosmos is to understand ourselves. For within us lies the universe, and in every distant star, we see a trace of our own existence. Imagine if you could see microwaves. Every night you'd witness something extraordinary. The faint glow of the Big Bang itself, still echoing across the universe. This faint cosmic light, known as the cosmic microwave background radiation, or CMB, is like an afterglow, the lingering embers of creation, reaching us even now, billions of years later. If we had microwave vision, we'd see the entire night sky ablaze with this ancient explosion, a reminder of that first powerful moment when the universe was born. In fact, you might have seen a glimpse of this Big Bang glow without even realizing it. When you switch your TV to an empty channel, a small portion of that static is the universe's first light, a direct remnant of the Big Bang. This cosmic radiation, though faint and scattered, holds answers to some of the universe's oldest mysteries. As the universe expands, it cools, and scientists have discovered that this cosmic radiation also tells us about a remarkable event that happened just moments after creation. Less than a trillionth of a second after the Big Bang, the universe entered a phase known as inflation, a period of rapid expansion faster than the speed of light. In this tiny instant, the fireball universe grew from the size of an atom to the size of a baseball. More expansion than it would see in the following billions of years. But if the universe started out so uniform, where did the stars and galaxies come from? For galaxies and planets to form, the early universe couldn't have been perfectly smooth. It needed tiny lumps of particles to grow over time, forming clusters that eventually gave rise to stars and planets. To uncover this, NASA scientists launched a mission with the Wilkinson Microwave Anisotropy Probe, or WMAP, in 2001. This satellite had a single mission: to map the temperature of cosmic radiation in unprecedented detail, capturing the tiniest variations across the sky. Orbiting 1,000,000 miles from Earth, WMAP observed the cosmos in incredible detail, revealing subtle ripples in temperature across the sky. These tiny variations, represented as blue and red spots on its cosmic map, showed areas of slightly different temperatures, places where particles first clumped together under gravity's pull, laying the groundwork for everything that would follow. These temperature ripples in WMAP's map are more than just colors. They're glimpses of the universe's baby picture, a snapshot from the first second of the Big Bang, revealing the seed patterns that formed galaxies, stars, and planets. The journey of understanding the universe is one of the greatest scientific adventures, and each discovery brings us closer to answering profound questions. What is the universe made of? How did it all begin? And what role do we play in this grand cosmic story? WMAP's picture may not be the face of God, as some have said, but it's something equally inspiring. A baby picture of the universe, a glimpse of the cosmos in its infancy. Have you ever wondered how all the matter around us formed in the Big Bang? In a nuclear explosion, particles of matter are torn apart to release enormous energy. But at the time of the Big Bang, the opposite happened. An enormous amount of energy turned into matter. Einstein's famous equation, E equals mc squared, helped us understand this transformation. As the early universe expanded and cooled, the pure energy of the Big Bang began to convert into the first particles of matter. Just a fraction of a second has passed, and the universe is already millions of times hotter than the sun's core. Yet, even at such extreme temperatures, particles were still too hot to bond and form atoms. Scientists compare this process to putting an ice cube in a steam bath. When the temperature is that high, nothing but the basic building blocks of matter can exist. If you were to travel back to those first seconds of the universe, your body would disintegrate instantly into subatomic particles. So how can scientists recreate these conditions from the Big Bang? The answer lies in particle accelerators. By colliding protons at nearly the speed of light, they can create temperatures similar to those that existed immediately after the Big Bang. At Brookhaven Laboratory in Long Island, the RHIC particle accelerator is used to collide gold nuclei, recreating the early universe on a small scale. These collisions produce a quark soup, the smallest particles that form matter, in a liquid state. As the early universe cooled from a sea of pure energy, the first particles of matter began to cluster. But there was a puzzle. When matter formed, it faced a special enemy: antimatter. Antimatter is the opposite twin of matter. When matter and antimatter meet, they annihilate each other in an explosion of energy. But somehow, matter won this battle, allowing the universe to exist as we know it. Why did matter prevail? Scientists are still investigating, but one theory suggests that antimatter may be less stable and decays faster, creating a tiny imbalance that allowed matter to dominate. By the end of the first second, the universe had cooled, and clumps of matter began to gather under the force of gravity, forming galaxies, stars, and planets. Yet, a great mystery remains. What gives particles their mass? Mass gives matter its shape and properties, and without it, the universe would be a diffuse sea of radiation with nothing to hold it together. Discovering the origin of mass in the first second is key to understanding the roots of life itself. If scientists can't identify the source of mass, the mystery of the first second will remain unsolved. The journey through the universe's first second is almost complete, but there's one missing piece, an enigma that puzzled scientists for decades. Then, in 1964, British physicist Peter Higgs proposed a groundbreaking theory. He suggested that an invisible force field sweeping across the universe in that first second gave particles their mass. This became known as the Higgs field. Particles that interact with this field gain mass. Think of it this way. Pushing a car on a road is fairly easy, but if it runs into mud, it suddenly feels heavier and harder to push. Scientists believe particles gain mass similarly. They push through the Higgs field, with some particles feeling heavier depending on how strongly they interact with it. The Higgs field is thought to carry its own unique particle. Journalists have nicknamed it the God particle, but scientists call it the Higgs boson. Identifying this particle could be the key to understanding how we came to exist. For decades, no particle accelerator was powerful enough to find the Higgs boson. Until now, deep beneath Geneva lies humanity's largest and most expensive experiment, the Large Hadron Collider, or LHC. It's the world's biggest particle accelerator and our best chance to find the missing Higgs boson. Built over 14 years, costing $10 billion, and involving over 7,000 scientists, the LHC is designed to recreate conditions from the universe's first second. By colliding protons at almost the speed of light, scientists hope to unlock one of the last mysteries of matter. The LHC features 4 enormous detectors along its 16-mile circular path. The Atlas detector, about half the length of a football field, is one of these and will be critical in the search for the Higgs. When protons collide within these detectors, the energy released mimics the intense conditions right after the Big Bang, producing showers of particles. Somewhere within this firestorm, scientists hope to find evidence of the elusive Higgs particle. Finding it, however, is like searching for a grain of gold on a beach. The Higgs boson is so fleeting that it can't be detected directly. Instead, scientists will look for its trail using the most sophisticated detectors in the world. Think of watching a skywriter. You see the smoke trail but never the plane itself. Similarly, these detectors will pick up the Higgs's trail and help us deduce its properties. The LHC will generate more data than any other instrument on Earth. Every second, the volume of data from these collisions surpasses the information held in all the libraries of the world. Processing this data requires the world's largest supercomputer network, and analyzing it may take years, but the potential impact is enormous. Finding the Higgs could mark the beginning of a new era in science. If the Higgs particle is not found, it would leave a gap in our understanding of the first second of creation, possibly requiring new theories and even more powerful experiments. One thing is certain. The LHC will take scientists closer to the Big Bang than ever before, reaching back 13.7 billion years to recreate the universe's first second, the most monumental second of all. Our cosmic clock completes its first second, The universe has cooled just enough for quarks to combine, forming protons and neutrons, the building blocks of everything we know. This first second set the entire course of history, establishing the foundation for stars, planets, and galaxies. In the next few minutes, protons and neutrons will form the first atomic nuclei. Within 300,000 years, the first atoms appear, and hundreds of millions of years later, the first stars ignite. 9 billion years after the Big Bang, Earth is born, all because of that single second, the genesis of everything. More than 12 billion years after the Big Bang, humanity emerges, a species with the intellect to ask, how did we get here, and what is the universe made of? This year, science moves closer than ever to answering these questions, and the secrets we seek lie in that first epic second of creation. Earth is unique in our solar system as the only planet with liquid water, 330 million cubic miles of it, covering over 70% of our surface, and even making up about 60% of our bodies. We know a lot about water, except for one mystery. Where does it come from? Scientists have long assumed that the building blocks of Earth were completely dry. If Earth formed without water, then where did our oceans come from? Solving this mystery is a bit like investigating a crime scene. From billions of years ago, the evidence has been altered, and scientists must piece together clues from deep in the past. For the first time, researchers from different fields are joining forces to trace the origins of Earth's water. Their findings have implications beyond our planet, touching on the very question of what makes a planet capable of supporting life. Around 4.6 billion years ago, the Sun was just a newborn star, encircled by a vast disk of gas and dust. Over millions of years, this disk condensed to form the planets. In the outer solar system, it was cold enough for planets like Jupiter to form with icy cores. Closer to the Sun, however, temperatures were over 1,000 degrees Fahrenheit, far too hot for water, and Earth likely formed dry from rocks and metals. One theory suggests that water may have arrived later, delivered by comets from the outer solar system. Comets are mostly ice, and for 600 million years, the young Earth was bombarded by countless icy comets. If true, this would mean that the water we drink, swim in, and that forms our bodies could be older than the planet itself, originating from the far reaches of the solar system. But this theory relies on more than guesswork. Scientists need concrete evidence. They've discovered that water molecules hold subtle clues about their origins, based on the type of hydrogen they contain. Most hydrogen atoms are light, but some are heavy with an extra neutron. By comparing the ratio of heavy to light hydrogen in Earth's water with that in comets, scientists hope to determine whether Earth's water truly came from comets. Halley's Comet offered the perfect opportunity. In 1986, scientists sent the Giotto probe to collect a sample from Halley's tail. When the results returned, they were shocking. The hydrogen in Halley's water had twice as much heavy hydrogen as the water on Earth. This discovery meant that comets likely didn't bring all of Earth's water, challenging the long-held comet theory. If comets didn't deliver Earth's water, where did it come from? In 2002, a groundbreaking discovery suggested the answer might be closer to home. By analyzing the oldest mineral ever found, a 4.4 billion-year-old zircon crystal, scientists realized it had formed in the presence of liquid water. This meant that Earth may have had water on its surface much earlier than previously thought. This surprising finding led researchers to consider an entirely new possibility. What if Earth's water was present from the very beginning? One theory proposes that water might have condensed onto dust grains in the protoplanetary disk, the gas and dust cloud from which Earth formed. Dr. Mike Drake tested this idea using olivine, a mineral abundant in the rocky planets. Surprisingly, his calculations showed that tiny olivine grains could absorb enough water vapor to account for up to 10 times the amount of water currently on Earth. This suggests that Earth's building blocks could have carried water all along, embedded in the minerals that formed the planet itself. Earth's oceans, rivers, and lakes, and even the water within us, might have been part of our planet from its very beginning, forming through an incredible process billions of years ago. The origins of Earth's water reveal not just the story of a single planet, but a key to understanding what makes worlds habitable. On this Earth, when our planet was still taking shape, billions upon billions of gallons of water already existed. These precious drops clung to trillions of dust particles in the vast cloud of gas and dust that would eventually become our blue planet. Professor Drake suggests that, from the earliest days of Earth, water has been an essential part, raising one of humanity's most fundamental questions: why do we have water? But his theory is new, and not everyone is convinced. It has a flaw, one even he can't fully explain. Our water has a unique signature, a specific ratio of heavy hydrogen to light hydrogen that reveals its origin. If water from outer space bore the same signature as Earth's, we would have solid evidence. However, the water from the gas and dust disks surrounding our young sun has a different signature. Though it looks identical to our water, it lacks the same concentration of heavy hydrogen. This raises a fascinating question. Could something else be at play? Indeed, mathematician Professor Morbidelli, with a fresh perspective, presents an entirely different theory on how water from the asteroid belt may have reached Earth. According to his view, space in our solar system is like an invisible web linking the planets, a gravitational push and pull. The precise positioning of massive planets like Jupiter influenced how asteroids, along with their water, were drawn toward Earth. A new model emerges, a model depicting the formation of all 8 planets at once. During this process, something extraordinary happened. Earth took shape from a mix of asteroids, some dry, some wet. Suddenly, everything fits. Our Earth ended up with water through this creative chaos. But the story doesn't end there. As Earth endured catastrophic collisions with large celestial bodies, the resulting heat and impact could have vaporized all its water. Yet somehow, water persisted. Where did Earth's water come from? And if there's extraterrestrial life, did those places experience a similar journey? In conclusion, this journey goes beyond just Earth. It opens the possibility of other worlds out there also possessing blue oceans and deep seas. Perhaps, as we uncover the origins of Earth's water, we simultaneously unlock the gateway to understanding the potential for life across distant stars. Gene a storm so powerful that it stretches over 200 miles, packing winds of over 100 miles per hour and capable of leveling entire cities in its path. This is the anatomy of a hurricane, a fearsome force of nature that scientists have studied for decades to understand, predict, and hopefully lessen its impact. In the last 10 years, hurricane hunters have deployed advanced probes that parachute directly into a hurricane's eye. As they descend, they measure temperature and humidity every half second. With the help of GPS, they capture wind speeds and directions, but the most crucial reading comes from the atmospheric pressure. In the center of the storm, pressure plummets, sucking in more warm, moist air and feeding the hurricane's ferocious cycle. As the storm strengthens, its eye contracts, making its winds even stronger. In 2005, Hurricane Wilma showed just how devastating this process could be. With a pinhole-sized eye, Wilma became one of the most intense storms in history. Scientists compare this contraction to an ice skater pulling in her arms to spin faster, ramping up the storm's power in a terrifying dance of physics. The hurricane's strength is classified by sustained wind speeds. At Category 1, winds of 74 to 95 miles per hour may only cause minor structural damage. But as it escalates to Category 5, winds surpass 155 miles per hour, demolishing buildings and flooding vast areas. Few things survive the brute force of a Category 5 hurricane. Meteorologists work tirelessly to track these storms, studying their dynamics to predict where and when they'll make landfall. They analyze the trade winds, which push the storm westward at up to 20 miles per hour, and the Bermuda High, a high-pressure dome that can steer the hurricane toward land or out to sea. It's a delicate balance of factors, where even a slight shift can mean the difference between safety and destruction. Computer models, powered by data collected over decades, now allow scientists to predict a hurricane's path with increasing accuracy. In the last 20 years, advancements in technology have improved track forecasts significantly. However, predicting a hurricane's intensity remains a challenge. But there's more to a hurricane than meets the eye. The storm's boundary layer, where sea meets sky, is where the real power lies. As it sucks up heat and moisture, this fuel intensifies the hurricane. Experiments like Sea Blast have provided critical data by flying through this boundary, but such missions come at a high risk. New technology, like unmanned probes, is now allowing scientists to measure the boundary layer without risking lives. As the hurricane nears landfall, it builds up a massive storm surge, responsible for nearly 90% of hurricane-related deaths. The surge, a wall of water that can exceed 20 feet, destroys everything in its path, making it one of the deadliest aspects of a hurricane. Katrina in 2005 demonstrated the sheer force of storm surges, overwhelming New Orleans and flooding entire neighborhoods. The hurricane's power didn't stop there. Its winds tore through towns, leaving trails of destruction. Yet even as it makes landfall, a hurricane's story isn't over. Moving inland, it weakens, starved of its oceanic fuel. But if it finds warm, moist land or shallow waters like the Everglades, it can revive, as Hurricane Andrew did before pounding Louisiana in 1992. Despite advancements, hurricanes remain a formidable challenge, and as climate change raises ocean temperatures, hurricanes may only grow stronger. Recent research shows that warmer oceans could lead to more intense hurricanes, making the work of meteorologists even more critical. With each discovery, they inch closer to understanding these storms, saving lives, and helping communities prepare. The anatomy of a hurricane is a stark reminder of nature's might. With the knowledge gained, scientists strive to predict these powerful storms, unveiling the secrets behind the birth, life, and death of Earth's most destructive forces. We may not be able to stop hurricanes, but by understanding them, we can learn to survive them, adding yet another piece to the puzzle of our dynamic planet. Imagine a powerful storm barreling down in the middle of winter, unleashing 87 tornadoes across 5 U.S. states, leaving a trail of devastation. This was February 5th, 2008, a day known as Super Tuesday. But this wasn't a typical tornado outbreak. It was a stark warning of how tornadoes are changing, becoming stronger, and striking outside traditional seasons and in areas once considered safe. That winter morning, meteorologists noted a rare mix of conditions. Cold, dry air swept down from the Rockies, colliding with warm air pushing north from the Gulf of Mexico, creating an unstable atmosphere primed for destruction. By afternoon, Huge, rotating thunderclouds called supercells began forming, stretching over Texas, Alabama, Kentucky, and beyond. These supercells, towering twice as high as Mount Everest, were an ideal birthplace for tornadoes. By nightfall, 87 tornadoes had torn across the central United States, claiming 57 lives and causing over $500 million in damage. As scientists began analyzing the tragedy, they faced an urgent question. How did these tornadoes form in winter? Typically, tornado season spans from spring to early summer. So what made Super Tuesday's storm so intense and deadly? Investigators turned to the sky, where the cold and warm air masses collided with a force that created a deadly spin called wind shear. This created the perfect conditions for tornadoes. But one of the biggest mysteries remained. Why did this storm generate so many violent tornadoes? Only 1 in 4 supercells spawns a tornado, and even fewer create the colossal ones seen on Super Tuesday. Scientists still search for the missing ingredient, a mysterious X factor that turns a storm into a tornado-making monster. When a tornado touches down, it becomes a vacuum for warm, moist air, feeding on this energy to grow stronger as it moves forward. The tornado's vortex pulls debris from the ground, creating a roar that sounds like a freight train. In Atkins, Arkansas, one of the worst tornadoes tore through 7 counties, killing 13 people and flattening entire neighborhoods. The sheer power of this tornado was shocking, especially in the dead of winter. To understand why tornadoes are happening more often outside their usual season, scientists looked at a strange ocean phenomenon called La Niña, a cooling event that happens thousands of miles away in the Pacific Ocean. Normally, tornadoes are more common in spring because of certain wind patterns. But during a La Niña year, cool winds from the northwest intensify and meet warm southern winds much earlier than usual. This increases the chances of severe winter storms like the Super Tuesday outbreak. Meteorologists discovered that during a La Niña year, there are more tornado outbreaks, and they tend to be more violent. 2008 was indeed a La Niña year, confirming a critical breakthrough. La Niña is directly connected to the increasing frequency of severe winter tornadoes. This revelation was a milestone in weather research, enabling meteorologists to predict future outbreaks more accurately and possibly save lives. Yet another mystery emerged. Why are today's tornadoes not only more frequent, but also more powerful? Scientists suspect that a key force, the jet stream, plays a crucial role. Moving at 300 miles per hour, the jet stream is an invisible, high-altitude ribbon of wind that helps steer and intensify storms. It forms where cool polar air meets warm equatorial air, pushing energy into storms as it flows. On Super Tuesday, the jet stream enhanced the storm's power, creating the perfect conditions for massive, long-lasting tornadoes. But there's hope. New radar technologies are giving scientists more insight than ever into the anatomy of these killer storms. Researchers are using phased array radar to capture the moment a tornado forms, potentially adding life-saving minutes to warning times. In the past, conventional radar took several minutes to scan a storm from top to bottom. But with phased array radar, multiple beams capture every detail, reducing the time needed to issue warnings. Armed with this knowledge, scientists are designing tornado-proof homes and tracking the formation of these storms with unprecedented accuracy. As they continue to unravel the mysteries of tornado formation, they hope to buy precious time to warn communities in harm's way. With each discovery, we get one step closer to understanding, predicting, and ultimately surviving the tornadoes of the future. Planet Earth has thrived for 4.5 billion years, a world shaped by cycles of birth, change, and survival. Yet forces are at work that will ultimately bring an end to everything we know. From giant asteroid impacts and catastrophic ice ages to the expansion of our sun, Earth will face 7 catastrophic events that push life to the brink and eventually erase all traces of humanity and life. Our story begins in the heavens. A 6-mile-wide asteroid barreling toward Earth could strike next year, or in 100 million years. But when it does, it will vaporize everything in its path, sending waves of destruction. But asteroids aren't the only threat. Imagine Earth covered in miles of ice, transforming continents into barren wastelands. In 30,000 years, a new ice age will begin, and temperatures will plunge, with vast ice sheets covering cities, leaving only small green belts for survival. 250 million years from now, Earth will be even more unrecognizable. Shifts in the tectonic plates will form a supercontinent, reshaping the world as we know it. Imagine this: 65 million years ago, a colossal asteroid, 1,000 billion tons of cosmic rock, streaks through the solar system and slams into Earth, triggering an explosion so immense that it wipes out the dinosaurs. These massive impact events, the kind that rewrite the story of life on our planet, occur once every 75 million years or so. But today, scientists continuously scan the night skies, on the lookout for what they call planet killers. And here's the unsettling truth. It wouldn't take an asteroid the size of a mountain to devastate us. A space rock just 150 feet wide, only as big as a small building, could obliterate a city the size of New York. What's even more unsettling? Right now, there's nothing we can do to stop it. Picture the nightmare. A gargantuan billion-ton asteroid hurtling towards Earth at 50,000 miles per hour. An unstoppable force bearing down with the energy of 300 million nuclear bombs. Enough power to wipe out humanity in a single impact. And here's the twist. This isn't some fantasy or nightmare. This is real. It's happened before that cosmic hammer fell on Earth 65 million years ago, erasing the dinosaurs from history. And while another monster impact may be millions of years away, smaller, city-destroying asteroids are far more common and far closer. In fact, around 50,000 years ago, one of these asteroids struck the Arizona desert with such force that it vaporized 175 million tons of rock in an instant. The result? A crater nearly a mile wide, 570 feet deep, blasted out of the desert floor. And the rock responsible was a mere 130 feet across, the size of a small jet plane. Here's the shocking part. These smaller asteroids are far more numerous, drifting unseen through the vastness of space, and any one of them could strike Earth with little warning. They pose a danger that most of us would rather not think about, but one scientist, Professor Ted Bunch from Northern Arizona University, believes this ancient Arizona crater tells a critical story. Events like this, he warns, are not just rare freak occurrences. They could happen at any time and are capable of massive destruction. He points to how the extreme heat of the asteroid's impact fused the desert sandstone into a glass-like material, an enduring reminder of the power held by a relatively small rock from space. Imagine the same thing happening in a city today. Picture an object 130 feet across, striking New York City. If it hit, the shock wave, heat, and seismic shock would devastate everything within a 5-mile radius. The skyscrapers, homes, subways, all would crumble in an instant. Scientists estimate that up to 80% of New Yorkers within that zone would suffer serious injuries or even death. The force, concentrated in one horrifying moment, would forever alter the landscape and lives of millions. Asteroids have been striking Earth since the planet's very formation. Their deadly power lies not just in their size, but in the way they convert velocity into pure, catastrophic energy. Hurtling through space at speeds of 50,000 miles per hour, even a modest-sized asteroid packs kinetic energy on a scale we rarely see on Earth. Think of a speeding car. The faster it goes, the more powerful its crash will be. But here's the cosmic difference. When a car hits a wall, it stops. When an asteroid hits Earth, all its energy detonates in one fiery, shattering moment. In Arizona, the evidence of such impacts stretches for miles. Pulverized rock fragments, called impactites, litter the landscape, blasted from the crater at speeds deadly to anything in their path. Each fragment is a grim reminder of how fragile our world is, a story of past collisions that scientists now study to better understand and, hopefully, prevent the next big impact. Imagine a futuristic battle against the mysteries of space. Scientists gather, proposing a dazzling plan, using nothing but sunlight, harnessed like a weapon, to save humanity from an asteroid on a collision course with Earth. Here's how they envision it. A powerful laser sears the surface of a rock, causing it to vaporize and shoot off gases. This effect is like strapping a rocket engine to an asteroid, but the beauty is that the asteroid becomes its own engine, shifting slowly but surely off its deadly path. Yet, to nudge an asteroid even slightly, you'd need a light source vastly stronger than any earthbound laser. Fortunately, we live near the sun, a cosmic powerhouse of energy. Here's the ingenious plan. Instead of using a single giant mirror to focus sunlight on the asteroid, scientists propose sending up a swarm of satellites, each equipped with smaller mirrors, working in unison to concentrate the sun's rays onto the rock. This focused light would create a controlled burst of vaporized rock, generating a gentle but persistent push. The plan is brilliant, but time is everything. Catching an asteroid early enough is key. Former astronaut Rusty Schweickart captures it best when he says, "Think about car insurance. You buy it just in case, even though the odds of an accident are low. But here we are, hurtling through space on Earth, totally uninsured against a cosmic accident." It's a reminder of how high the stakes are. We've had brushes with disaster. In 2007, villagers in Caracas, Peru, witnessed a mysterious fireball tearing through the sky, ending with a massive explosion and a crater 50 feet wide. People thought it was a military attack, but scientists suspected an asteroid. The crater was small, barely scratching Earth's atmosphere, which usually incinerates such small rocks. Yet, somehow, this rock had survived, blasting through the atmosphere and leaving its mark. Asteroid expert Peter Schultz couldn't believe his eyes when he visited the site. The crater, though tiny, bore all the hallmarks of an asteroid impact. After analyzing fragments, he discovered something even more unsettling. This space rock, only a few feet across, hit Earth with terrifying force. If something this small could survive entry and strike with such power, what might happen if it hit a crowded city? This discovery was a wake-up call for Schultz and many others. Even small asteroids, those a mere 3 to 6 feet across, could reach Earth's surface and wreak havoc. If one landed in a populated area, the consequences could be disastrous, potentially penetrating several floors of a skyscraper. Schweickart believes now is the time to take the threat seriously. Think about it, he says. For hurricanes, we can't prevent them. but we can prepare. For asteroid impacts, we have the unique opportunity to prevent disaster. With the right technology, we could avoid catastrophe altogether. In the near future, humanity may face a test like never before, a race against time to prevent an asteroid from striking Earth. But will we be ready when that day comes, Doctor? Jeff Cozy is at Mission Control as the Cassini spacecraft approaches the gap between Saturn's rings. The gap isn't visible to the naked eye, making it a tense and precise maneuver. Cassini must thread the needle through this invisible sliver of space. All eyes are glued to the monitors as the spacecraft fires its rocket engines, aligning itself for this risky crossing. Then, as Cassini angles into position, its antenna turns away from Earth, and Mission Control loses contact. Dr. Larry Esposito waits, watching the screen for the all-important signal that Cassini has survived the passage. In the room, the silence is thick. Everyone is holding their breath. Finally, after hours that feel like an eternity, the signal returns. Cassini has successfully navigated the ring plane. The room erupts with applause and cheers. Decades of planning have culminated in a single, breathtaking moment. Humanity's first spacecraft is now orbiting a planet in the outer reaches of the solar system. Dr. Tony Delano, one of the mission's lead scientists, knows this is a new era for planetary exploration. The beauty of the Cassini mission is that for the first time, we get to orbit a planet like Saturn, observing it from all angles over years, he explains. This long-term mission allows scientists to study the gas giant in unprecedented detail. Cassini's first target is Saturn's South Pole, where it captures images of a massive storm swirling like a hurricane. This isn't an ordinary storm. It's 1,000 miles wide, with winds whipping at over 350 miles per hour. The towering eye wall rises 45 miles high, and temperatures here plummet to minus 167 degrees Fahrenheit, creating ice crystals that float down like snow. Dr. Esposito remarks that Saturn's storms, like Earth's hurricanes, seem eerily familiar, complete with swirling clouds, fierce winds, and frozen precipitation. But unlike Earth's storms, which are powered by the sun, Saturn is too far from our star to rely on solar energy. Scientists theorize that the power for these storms must come from deep within Saturn itself. To test this idea, astrophysicist Dr. Peter Reed from France's Coriolis laboratory recreates Saturn's turbulent atmosphere in a giant tank filled with liquid. With heat applied at the base, the fluid mimics Saturn's gases, swirling into currents and vortices similar to the patterns Cassini has observed on Saturn. This experiment strengthens the theory. Saturn's storms are likely driven by heat from deep within the planet. Deep down, where pressures reach millions of times that of Earth's surface, hydrogen gas transforms into a strange, metallic liquid. Scientists believe that as helium sinks through this dense hydrogen, it creates friction and generates the internal heat that fuels Saturn's massive storms. Cassini is on the lookout for proof, measuring the levels of helium in Saturn's atmosphere to confirm this hypothesis. After capturing stunning views of Saturn's roiling atmosphere, Cassini's main engines fire again, and Mission Control redirects it to explore Saturn's rings, a chaotic belt of ice and rock fragments circling the gas giant. These rings, first imaged by the Voyager probes decades ago, are like a turbulent cosmic river. Small fragments, some only inches across, collide and shift constantly, while larger chunks drift in and out of clusters. Cassini's instruments reveal something astonishing. The particles often clump together into temporary moonlets, small agglomerations that break apart and reform under the influence of Saturn's gravity. These images offer a glimpse back in time to the early days of our solar system. The moonlet's behavior resembles the process that may have created planets billions of years ago, as particles around the young sun clump together, growing larger over millions of years until planets emerged. One of the biggest mysteries Cassini seeks to unravel is the origin of Saturn's rings. Scientists believe the rings may be the remains of a moon shattered in a collision eons ago. Saturn's powerful gravity could have gathered the fragments into a flat ring around its equator, forming the mesmerizing rings we see today. These remnants of ancient cosmic violence may also hold clues to the solar system's birth 4.5 billion years ago. Next, Cassini turns to an equally enigmatic world, Titan, Saturn's largest moon. Carrying a smaller probe named Huygens, designed to land on Titan's mysterious surface, Cassini will embark on a journey to reveal what lies beneath Titan's thick atmosphere. Titan's massive size and dense, smoggy atmosphere have long intrigued scientists. The data from Cassini and Huygens may hold answers about the conditions that existed on early Earth, possibly providing clues about how life might arise in the universe. Cassini's mission has already reshaped our understanding of Saturn, and it's only just begun. As it continues to capture images and data, the spacecraft unlocks more secrets of Saturn, its rings and its moons, one revelation at a time. Picture an alien world shrouded in thick orange haze. This is Titan, Saturn's largest moon, and scientists are mesmerized by its atmosphere, filled mostly with nitrogen, just like Earth's. But there's more. Cassini detects traces of organic molecules, such as ethane and carbon dioxide, compounds that could be the building blocks of life. This atmosphere is eerily similar to what Earth's own may have looked like billions of years ago. Now, the Huygens probe, carried by Cassini, is set to pick up where Voyager left off, plunging through Titan's mysterious clouds to search for signs of life. For Dr. Carolyn Porco, who worked on the original Voyager mission, returning to Saturn after decades is an exhilarating moment. Cassini's cameras, however, struggle to penetrate Titan's thick atmosphere, capturing only hints of the world below. But as Huygens descends, it transmits the first clear images of the moon's surface. Dr. Ralph Lorenz, a mission engineer, watches with anticipation, unsure what lies below. Would Huygens land on a lake of methane or a barren, icy plain? Incredibly, it touches down on solid ground, becoming the first probe to reach another world in the outer solar system. The images reveal a landscape unlike any other, a vast, desert-like plain scattered with smooth, rounded rocks, reminiscent of a dried riverbed. Lorenz's instruments analyze the ground, which feels like damp sand or soft clay. The data suggests Titan once had flowing liquid, possibly carving these rocks over time. But what liquid could exist here? Titan's surface temperature is a bone-chilling minus 290 degrees Fahrenheit, freezing water into a rock-hard solid. As Huygens explores further, Cassini shifts its focus to Titan's North Pole. Using radar, it finds dark patches, lakes of liquid methane. It seems that methane, not water, has shaped this moon's riverbeds and canyons. In Titan's sub-zero environment, methane exists as a liquid, raining down from massive clouds to fill lakes and carve the landscape. The moon's atmosphere is filled with complex organic molecules, including tholins, compounds essential to life's chemistry on Earth. Dr. Chris McKay, an astrobiologist, tries to recreate Titan's atmospheric conditions in his lab. He starts with methane and nitrogen, subjects them to simulated ultraviolet radiation, and watches as simple molecules evolve into complex, nitrogen-rich tholins, almost identical to those on Titan. McKay's findings lead him to wonder, if this kind of chemistry is common on Titan, could it have occurred on early Earth? If so, might this process be universal? Could life emerge on any world with similar conditions? Cassini and Huygens have provided tantalizing clues about life's potential beyond Earth. But Cassini's journey isn't over. The spacecraft sets its sights on another of Saturn's moons, Enceladus, a tiny, icy world that hides an incredible secret. As Cassini approaches Enceladus, its instruments detect a strange signal: giant plumes of vapor erupting from cracks near the moon's south pole. These geysers shoot over 400 miles into space, filled with water vapor, nitrogen, and organic molecules. The discovery is astonishing. Beneath Enceladus's frozen surface, there could be a warm ocean, perhaps with the potential to harbor life. Scientists believe that the heat necessary to sustain this ocean may come from tidal forces as Enceladus orbits Saturn. The constant flexing generates enough friction to melt ice, creating pockets of warm, liquid water. Cassini flies through the plumes, analyzing their composition and finding hints of a world that might be as vibrant as the oceanic depths on Earth, where primitive life thrives around hydrothermal vents. The potential for life on Enceladus is breathtaking. If organisms could survive in the moon's hidden ocean, it would be one of humanity's greatest discoveries. Dr. Porco reflects, imagine finding life beyond Earth, proof that we're not alone. If it happened on Enceladus, it could happen throughout the universe. As Cassini orbits Saturn, it continues to unlock secrets that could change our understanding of life's potential in the cosmos. With each discovery, it draws us closer to answering one of humanity's oldest questions. Are we alone in the universe? The journey has only just begun. Imagine Earth shielded like a fortress by a vast magnetic bubble, the magnetosphere, that wraps around the planet, protecting us from the deadly cosmic radiation streaming through the solar system. This invisible shield deflects the high-energy particles coming from the sun, known as the solar wind, which, if allowed to reach Earth's surface, could pose a serious hazard to life. Without this protective barrier, living organisms would be exposed to harmful radiation. These particles can penetrate tissues, causing cellular damage that can lead to cancer, and they even alter DNA, the very blueprint of life. But now, scientists are observing an unsettling change. Earth's magnetic field is weakening. Dr. Mario Acuna from NASA explains how Earth's field behaves like a bar magnet, with lines stretching out from the magnetic South Pole and looping back into the magnetic North Pole. Deep below Earth's surface, around 3,000 miles down, this field is generated and projected outward, forming the magnetosphere that envelops us. Yet there's an anomaly, a rapidly weakening section of the magnetic field. It spans roughly 3 million square miles over the South Atlantic, stretching from Brazil across the ocean, where cosmic radiation is beginning to seep closer to Earth's surface. This area, known as the South Atlantic Anomaly, is growing, creating an increasingly intense radiation zone. NASA scientists have found that satellites passing over this region experience disruptions, and even the billion-dollar Hubble Space Telescope must shut down sensitive instruments when crossing this area. Experts warn that if the field continues to weaken, not only will technology be at risk, but passengers flying at high altitudes could experience higher radiation levels. Professor Peter Olson explains, passengers flying over weakened regions of the magnetic field could be exposed to more radiation. impacting communications and possibly endangering lives. As Earth's magnetic field diminishes, the consequences could be severe, affecting life on the ground and in the air. To understand what might happen if Earth's magnetic field continues to weaken, scientists look to Mars. Billions of years ago, Mars likely had a magnetic field, but it vanished over time. The result? Mars lost its atmosphere, its water evaporated, and the surface became a frozen desert. Without its protective magnetic shield, the solar wind stripped away Mars's atmosphere, cooling the planet and making it inhospitable for any potential life forms. Earth, however, still has a magnetic field, and scientists are racing to understand how it is generated. Dr. Ben Weiss and his team analyze Martian meteorites to uncover how Mars's magnetic field once behaved. These rocks, ejected from Mars and landing on Earth as meteorites, reveal that in its early years, Mars had a magnetic field similar in strength to Earth's. But over time, Mars's field faded, leading to catastrophic changes. As Earth's magnetic field continues its mysterious decline, scientists like Professor Jeremy Bloxham are calculating how long we have before it could disappear entirely. If the current rate of decay persists, Earth's magnetic shield might vanish in 1,500 years. Without this shield, Earth could one day face the same fate as Mars, exposed to the relentless cosmic radiation that fills space. This shift in Earth's magnetic protection isn't just a scientific curiosity. It's a race against time. Imagine the Earth as a vast, dynamic sphere with layers stretching deep into its core, like a giant rocky onion. To peer inside, scientists don't use a scalpel, they listen. When an earthquake occurs, seismologists place arrays of detectors on the other side of the globe to hear the vibrations, or seismic waves, as they pass through Earth's layers. These waves bend, slow, and change direction based on the materials they encounter, allowing scientists to map Earth's hidden structure. What they've discovered is remarkable. Beneath the surface, crust, lies the mantle, a layer of semi-liquid rock stretching down 1,800 miles. Below that, the outer core churns as a sea of molten iron and nickel, surrounding an inner core, a solid iron sphere about the size of our moon, with temperatures rivaling the sun's surface. This inner core, scientists believe, generates Earth's magnetic field. But how? The mystery lies in a phenomenon called the geodynamo. Professor Dan Lathrop at the University of Maryland tackles this by constructing a massive 10-foot mechanical model of Earth's core. Inside the model is a solid iron ball surrounded by 13 tons of molten sodium. Sodium mimics Earth's molten iron, but melts at a much lower temperature, allowing Lathrop and his team to simulate Earth's core activity. As the model spins, reaching speeds of 15 revolutions per second, something extraordinary happens. Arcs of magnetism spring from the core. Lathrop watches as these magnetic lines flow, twist, and shift, revealing the dynamic power of the geodynamo, a self-sustaining magnetic field generated by the movement of molten metal. This magnetic dynamo is what protects life on Earth. But here's the concern. Mars, once thought to have had a magnetic field, lost its geodynamo long ago. Without this shield, Mars was left exposed to the sun's radiation, its atmosphere stripped away, and its oceans vanished. Now, scientists wonder if Earth could face a similar fate. Though Earth's core remains hot enough to power the geodynamo, it's slowly cooling. As this happens, the molten core could eventually solidify, potentially causing the magnetic field to shut down. Signs like the South Atlantic anomaly, a growing region of weak magnetism over the South Atlantic Ocean, have scientists on edge. Could this be a hint of Earth's field weakening, or even reversing? Professor Jeremy Bloxham has uncovered another clue. By analyzing historical records of magnetic north taken by early sailors, he charts how magnetic north has drifted and shifted over the centuries. Using computer models, he visualizes Earth's magnetic history and finds something unusual. In the South Atlantic, the magnetic field has not only weakened but also reversed. This area, known as the South Atlantic Anomaly, allows cosmic radiation to penetrate further, reaching the upper atmosphere. If the field continues to weaken, the consequences could be profound. Cosmic radiation would reach lower altitudes, impacting satellites, aircraft, and potentially life itself. Some scientists believe this weakening might be a precursor to a magnetic reversal, where the North and South poles swap places, a phenomenon seen in simulations but never witnessed in real time. And what if this is the start of a reversal? As the poles flip, our magnetic shield would shrink, exposing Earth to higher levels of cosmic radiation for thousands of years. While this change might not happen overnight, the implications are profound, prompting scientists to study every clue they can find, from computer models to ancient lava flows in Hawaii, hoping to unlock the secrets of Earth's magnetic heart before it's too late. Imagine hiking through ancient lava flows on a Hawaiian volcano. To most, it's a landscape of hardened rock, but for Professor Emilio Herrero Vera, each layer is a chapter in Earth's magnetic history. Here, thin, stacked lava flows serve as time capsules, preserving snapshots of Earth's magnetic field from millions of years ago. Welcome to the dark side of the universe, where the deepest mysteries await discovery. Here, we embark on a hunt for the ultimate cosmic beasts, black holes. While scientists scan the heavens with telescopes, advanced computer simulations are unraveling the strange and powerful secrets of these celestial enigmas, capable of bending space and time. Let's venture beyond the point of no return, into what nature calls the ultimate forbidden zone. This is a journey into the most awe-inspiring corners of the universe. We'll start right in our cosmic neighborhood. The Milky Way, home to hundreds of billions of stars, is just one of over 100 billion galaxies in the universe. Our Sun is merely one among countless stars. Once, we saw stars as welcoming beacons lighting the vast darkness of space. Now, we understand the universe is as fierce as it is beautiful. Out there lie forces of unimaginable violence, capable of tearing apart space and time itself. And today, we'll step closer to understanding one of its most powerful phenomena: black holes. Black holes, masters of disguise. At Cape Canaveral, Florida, an extraordinary mission is underway. A telescope called SWIFT is being launched into space, carrying the hopes of scientists eager to uncover the secrets of black holes, elusive entities that hide in the depths of the universe. Black holes are unique because they allow no light to escape, making them nearly impossible to detect. But SWIFT has a strategy. It searches for gamma rays, bursts of intense energy that occur when a black hole is born. These explosions are triggered by the death of massive stars in events known as supernovas, brighter than 1 billion suns combined. What powers these incredible events? Gravity. Long ago, scientists believed gravity was a mysterious force projected by objects like the sun across space. Then Albert Einstein changed everything. He showed that gravity is actually the result of the bending of space-time, a four-dimensional fabric that makes up the universe. Massive objects like stars create dents in this fabric, pulling smaller objects into orbit around them. Superstars, the birthplace of black holes. Einstein's ideas become even more fascinating when applied to extreme cases like red supergiants, stars more than 25 times the mass of our Sun. These giants live fast and die young, burning brightly for only a few million years, compared to the billions of years in our Sun's lifespan. Deep in their cores, gravity crushes matter together, driving temperatures above 1 billion degrees. Light elements like hydrogen fuse into heavier ones like helium, carbon, and eventually iron. When the core becomes too heavy to sustain itself, it collapses. The resulting implosion sends a shock wave outward, causing a massive supernova explosion. What's left behind is a black hole, an object so dense and compact that its gravitational pull becomes inescapable. Close to a black hole, gravity intensifies dramatically, pulling everything toward it. As you approach, it's like being caught in a powerful river current, dragging you faster and faster toward an enormous waterfall. This critical edge, beyond which nothing can escape, is called the event horizon. Black holes, not as rare as you think. It might surprise you, but black holes aren't that rare. In the Milky Way alone, astronomers have detected dozens and estimate there are millions more. But there's another type of black hole that's even more extraordinary: supermassive black holes, lurking at the centers of nearly all large galaxies. One of the most remarkable examples resides in the M87 galaxy, millions of light-years away. This black hole is 4 billion times the mass of our Sun and emits a jet of energy shooting into space at nearly the speed of light. How did such colossal black holes form? To find out, we rewind the cosmic clock back to 14 billion years ago, when the universe began with the Big Bang. Matter and energy surged outward, and over time, gravity began pulling gas and dust together. This process eventually gave birth to the first stars. As these stars burned out and exploded in supernovas, they left behind the first black holes. These black holes migrated to the centers of their galaxies, where they consumed gas, dust, and stars, growing larger over billions of years. When galaxies collided, their central black holes merged, creating even more massive entities. The immense waves of energy released during these mergers could shape galaxies, determining their size, structure, and even distributing essential elements like carbon, oxygen, and iron, the building blocks of life. The Milky Way's hidden giant. What about our own Milky Way? Do we harbor a supermassive black hole too? To answer this, astronomer Andrea Ghez and her team have spent over a decade observing the center of our galaxy from the Keck Observatory in Hawaii. By tracking the movements of stars near the galactic core, they've discovered something extraordinary. These stars are orbiting a hidden object at astonishing speeds, up to 3 million miles per hour. Using their calculations, Gez's team determined the object's mass to be 4 million times that of our Sun. Though invisible, this is definitive evidence of a supermassive black hole at the heart of the Milky Way. While we can't see it directly, knowing it's there raises a tantalizing question. What would it be like up close? Though no spacecraft is heading there yet, our curiosity drives us to imagine and explore. The mysteries of the universe are vast, and black holes are just the beginning. So, are you ready to uncover the secrets of the cosmos? Let the journey begin. We're about to embark on an extraordinary journey to the heart of the Milky Way, guided by the latest telescope observations and advanced computer models. Imagine leaving the quiet suburb of our solar system, nestled halfway out from the galaxy's center. Before us stretches the majestic Milky Way, a celestial highway so vast it would take a beam of light 100,000 years to travel from one end to the other. Our destination? The galaxy's bustling core, known as the bulge, where stars pack together in a dazzling, chaotic hub. The closer we move toward the center, the more crowded the space becomes. Dust, stars, and hot gas jostle for room, creating a cosmic traffic jam that never lets up. It's rush hour on a galactic scale. As we approach the dead center, chaos intensifies. Signs of ancient destruction litter the way. Supernova remnants and swirling clouds, a testament to violent forces at play. Astronomers like Andrea Ghez have mapped this cosmic terrain using light that ranges from invisible radio waves to powerful X-rays. But here, their observations hit a limit. We enter a zone dominated by the insatiable appetite of a lurking giant, a black hole. Surrounding it is a swirling cloud of super-hot gas, a chaotic dance of matter being pulled in by the black hole's immense gravity. Yet, not everything is devoured. Much of this gas is hurled back out into space, creating a spectacle that's as strange as it is fascinating. What you're seeing isn't Hollywood CGI, it's real science, the first time we've visualized the incredible journey into a black hole. Guided by Einstein's groundbreaking equations, we learn that the space near a black hole is so warped that it acts like a giant lens, bending and twisting light around it. As we move closer, we cross the event horizon, the infamous point of no return. Beyond this boundary, not even light can escape the black hole's gravitational grip. But contrary to popular belief, the inside of a black hole isn't pitch black. It's an intense maelstrom of energy and matter swirling in unimaginable chaos. At the core of this chaos lies the singularity, a point where all the black hole's mass is compressed into an infinitely small, infinitely dense space. Here, the laws of physics as we know them break down. But let's imagine for a moment that we could tame this chaos, creating a calm eye within the storm. What might we find? Perhaps, as Einstein's equations suggest, there's a passage, a theoretical wormhole, leading to another place, or maybe even another universe. On the other side could lie a white hole, where the logic flips. Instead of drawing matter in, it flings everything out. It's the stuff of science fiction dreams, a cosmic escape hatch through space and time. But in reality, black holes are far too violent and unstable for wormholes to form, let alone allow safe passage. They are the ultimate forces of destruction in the universe. Or are they? When this black hole was young, it may have played a pivotal role in shaping our galaxy. Its powerful winds likely scattered elements across space, carbon, oxygen, iron, seeding the galaxy with the building blocks for stars, planets, and life itself. In a way, these engines of destruction also give life, fueling the restless cycle of creation in the cosmos. And so, as we ponder what lies within, we realize black holes are not just terrifying voids. They're a window into the universe's most profound mysteries, challenging us to unlock secrets stolen from the edge of infinity. Welcome to the dark side of the universe, where the deepest mysteries await discovery. Here, we embark on a hunt for the ultimate cosmic beasts, black holes. While scientists scan the heavens with telescopes, advanced computer simulations are unraveling the strange and powerful secrets of these celestial enigmas capable of bending space and time. Let's venture beyond the point of no return into what nature calls the ultimate forbidden zone. This is a journey into the most awe-inspiring corners of the universe. We'll start right in our cosmic neighborhood. The Milky Way, home to hundreds of billions of stars, is just one of over 100 billion galaxies in the universe. Our Sun is merely one among countless stars. Once, we saw stars as welcoming beacons lighting the vast darkness of space. Now, we understand the universe is as fierce as it is beautiful. Out there lie forces of unimaginable violence, capable of tearing apart space and time itself. And today, we'll step closer to understanding one of its most powerful phenomena: black holes. At Cape Canaveral, Florida, an extraordinary mission is underway. A telescope called SWIFT is being launched into space, carrying the hopes of scientists eager to uncover the secrets of black holes, elusive entities that hide in the depths of the universe. Black holes are unique because they allow no light to escape, making them nearly impossible to detect. But SWIFT has a strategy. It searches for gamma rays, bursts of intense energy that occur when a black hole is born. These explosions are triggered by the death of massive stars in events known as supernovas, brighter than 1 billion suns combined. What powers these incredible events? Gravity. Long ago, scientists believed gravity was a mysterious force, projected by objects like the sun across space. Then Albert Einstein changed everything. He showed that gravity is actually the result of the bending of space-time, a four-dimensional fabric that makes up the universe. Massive objects like stars create dents in this fabric, pulling smaller objects into orbit around them. Einstein's ideas become even more fascinating when applied to extreme cases, like red supergiants, stars more than 25 times the mass of our Sun. These giants live fast and die young, burning brightly for only a few million years, compared to the billions of years in our Sun's lifespan. Deep in their cores, gravity crushes matter together, driving temperatures above 1 billion degrees. Light elements like hydrogen fuse into heavier ones like helium, carbon, and eventually iron. When the core becomes too heavy to sustain itself, it collapses. The resulting implosion sends a shock wave outward, causing a massive supernova explosion. What's left behind is a black hole, an object so dense and compact that its gravitational pull becomes inescapable. Close to a black hole, gravity intensifies dramatically, pulling everything toward it. As you approach, it's like being caught in a powerful river current, dragging you faster and faster toward an enormous waterfall. This critical edge, beyond which nothing can escape, is called the event horizon. It might surprise you, but black holes aren't that rare. In the Milky Way alone, astronomers have detected dozens and estimate there are millions more. But there's another type of black hole that's even more extraordinary: supermassive black holes lurking at the centers of nearly all large galaxies. One of the most remarkable examples resides in the M87 galaxy, millions of light years away. This black hole is 4 billion times the mass of our Sun and emits a jet of energy shooting into space at nearly the speed of light. How did such colossal black holes form? To find out, we rewind the cosmic clock back to 14 billion years ago, when the universe began with the Big Bang matter, and energy surged outward. And over time, gravity began pulling gas and dust together. This process eventually gave birth to the first stars. As these stars burned out and exploded in supernovas, they left behind the first black holes. These black holes migrated to the centers of their galaxies, where they consumed gas, dust, and stars, growing larger over billions of years. When galaxies collided, their central black holes merged, creating even more massive entities. The immense waves of energy released during these mergers could shape galaxies, determining their size, structure, and even distributing essential elements like carbon, oxygen, and iron, the building blocks of life. What about our own Milky Way? Do we harbor a supermassive black hole too? To answer this, astronomer Andrea Ghez and her team have spent over a decade observing the center of our galaxy from the Keck Observatory in Hawaii. By tracking the movements of stars near the galactic core, they've discovered something extraordinary. These stars are orbiting a hidden object at astonishing speeds, up to 3 million miles per hour. Using their calculations, Gez's team determined the object's mass to be 4 million times that of our Sun. Though invisible, this is definitive evidence of a supermassive black hole at the heart of the Milky Way. While we can't see it directly, knowing it's there raises a tantalizing question. What would it be like up close? Though no spacecraft is heading there yet, our curiosity drives us to imagine and explore. The mysteries of the universe are vast, and black holes are just the beginning. So, are you ready to uncover the secrets of the cosmos? Let the journey begin. We're about to embark on an extraordinary journey to the heart of the Milky Way. Guided by the latest telescope observations and advanced computer models, imagine leaving the quiet suburb of our solar system, nestled halfway out from the galaxy's center. Before us stretches the majestic Milky Way, a celestial highway so vast it would take a beam of light 100,000 years to travel from one end to the other. Our destination? The galaxy's bustling core, known as the bulge, where stars pack together in a dazzling, chaotic hub. The closer we move toward the center, the more crowded the space becomes. Dust, stars, and hot gas jostle for room, creating a cosmic traffic jam that never lets up. It's rush hour on a galactic scale. As we approach the dead center, chaos intensifies. Signs of ancient destruction litter the way. Supernova remnants and swirling clouds, a testament to violent forces at play. Astronomers like Andrea Ghez have mapped this cosmic terrain using light that ranges from invisible radio waves to powerful X-rays. But here, their observations hit a limit. We enter a zone dominated by the insatiable appetite of a lurking giant, a black hole. Surrounding it is a swirling cloud of super-hot gas, a chaotic dance of matter being pulled in by the black hole's immense gravity. Yet, not everything is devoured. Much of this gas is hurled back out into space, creating a spectacle that's as strange as it is fascinating. What you're seeing isn't Hollywood CGI, it's real science, the first time we've visualized the incredible journey into a black hole. Guided by Einstein's groundbreaking equations, we learned that the space near a black hole is so warped that it acts like a giant lens, bending and twisting light around it. As we move closer, we cross the event horizon, the infamous point of no return. Beyond this boundary, not even light can escape the black hole's gravitational grip. But contrary to popular belief, the inside of a black hole isn't pitch black. It's an intense maelstrom of energy and matter, swirling in unimaginable chaos. At the core of this chaos lies the singularity, a point where all the black hole's mass is compressed into an infinitely small, infinitely dense space. Here, the laws of physics as we know them break down. But let's imagine for a moment that we could tame this chaos, creating a calm eye within the storm. What might we find? Perhaps, as Einstein's equations suggest, there's a passage, a theoretical wormhole, leading to another place, or maybe even another universe. On the other side could lie a white hole, where the logic flips. Instead of drawing matter in, it flings everything out. It's the stuff of science fiction dreams, a cosmic escape hatch through space and time. But in reality, Black holes are far too violent and unstable for wormholes to form, let alone allow safe passage. They are the ultimate forces of destruction in the universe. Or are they? When this black hole was young, it may have played a pivotal role in shaping our galaxy. Its powerful winds likely scattered elements across space: carbon, oxygen, iron, seeding the galaxy with the building blocks for stars, planets, and life itself. In a way, these engines of destruction also give life, fueling the restless cycle of creation in the cosmos. And so, as we ponder what lies within, we realize black holes are not just terrifying voids. They're a window into the universe's most profound mysteries, challenging us to unlock secrets stolen from the edge of infinity. The Gulf Stream, often called a great ocean river, winds its way along the coast of North America, carrying an unimaginable amount of heat, enough to power the industrial world 100 times over. As it travels, it breaks into massive whirlpools, spreading warm tropical waters to northern seas. Beneath the surface, these warm currents mix with colder, deeper ones, swirling around undersea mountains and ledges, creating a complex system that drives Earth's climate engine. This climate system is a masterpiece of nature, with countless moving parts: tides, winds, ocean currents, and the very shape of the seafloor, all working together to balance temperatures around the globe. But when tropical heat builds up beyond what the system can handle, the result is explosive. In August 2005, the Gulf Stream spawned one of the most destructive hurricanes in history, Katrina. Using supercomputer models, scientists have reconstructed Katrina to better understand how hurricanes work. Virtual streamers reveal the storm's dynamics, showing warm winds rising and colliding with cooler air above. This interaction produces massive clouds while increasing the evaporation of warm seawater. The storm draws more heat from the ocean, fueling its winds, which then accelerate further. Around the eye of the hurricane, these winds can reach terrifying speeds of 250 kilometers per hour. The sheer power of hurricanes is staggering. A storm like Katrina can release as much heat energy in just 20 minutes as a 10-megaton nuclear bomb. Yet hurricanes are more than destructive forces. They also play a role in Earth's climate. The moisture they stir into the atmosphere helps retain heat, much like a blanket, thanks to water vapor and carbon dioxide, CO2, two critical greenhouse gases. Unlike Venus, where CO2 has trapped enough heat to turn the planet into a scorching cauldron, Earth has a secret weapon to keep its CO2 levels in check: life. The oceans are brimming with microscopic heroes, phytoplankton. These tiny organisms might be invisible to the naked eye, but they are essential for our planet's survival. They absorb CO2 from the atmosphere, releasing oxygen in return. The carbon they store begins a journey through the food chain, starting with zooplankton, then small fish, and on to larger predators like tuna, sharks, and even whales. At every step of the food chain, carbon moves upward, building in mass. One of the largest players in this cycle, the humpback whale, consumes up to 1.5 tons of food daily, storing vast amounts of carbon in its enormous body. From the tiniest phytoplankton to the mighty whales, marine life forms a global system that not only removes CO2 from the atmosphere, but also stores it deep in the ocean. Some of this carbon settles on the seafloor, where over time it transforms into oil, limestone, or sedimentary layers. This process locks carbon away for millions of years, until natural forces like erosion or volcanic activity release it back into the atmosphere. This constant cycle of absorption and release is what has kept Earth habitable for so long. But today, the carbon cycle is under stress. Human activities, especially the burning of fossil fuels, have thrown this delicate balance out of sync. Since the Industrial Revolution, atmospheric CO2 levels have risen nearly 40%, most of it in just the past 50 years. This surge has already caused global temperatures to rise by nearly 1 degree Celsius, accelerating the melting of polar ice and raising sea levels. The Arctic, once a vast expanse of ice, has lost a quarter of its summer coverage since the 1980s. What's left is thinner and more vulnerable. As the ice melts, regions experience shifting weather patterns. Some face intense rainfall, others prolonged droughts. Deserts expand, forests recede, and coastlines are at risk of disappearing under rising seas. Earth's systems are resilient, but they're not immune to the pressures we place on them. The choices we make now, how we treat the oceans, the atmosphere, and the life they sustain, will determine whether our planet remains a thriving haven or becomes a cautionary tale of imbalance. The future is in our hands. From the vantage point of space, Earth reveals its intricate beauty, an elaborate web of climate systems working together to nurture life. Technology has gifted us the ability to map these interconnected systems, the winds, waters, and tectonic forces that protect and sustain our world. Within this delicate dance of nature lies Earth's greatest marvel, life itself. Our planet's story, woven through time, is one of survival and renewal. But today, we find ourselves at a crossroads, asking the ultimate question: will we exhaust Earth's resources, or will we save it? Beneath the surface, however, lies another tale, a tale of unimaginable fury and creation. Welcome to the world of supervolcanoes. These are no ordinary eruptions. They are colossal events, so powerful they have shaped Earth's history, bringing mass extinctions, collapsing climates, and unleashing toxic chaos. To understand their might, we must look back in time. Travel with me to 74,000 years ago, to the island of Sumatra, where the Earth itself seemed to tremble with anticipation. Along the eastern rim of the Indian Ocean, tremors rattled the landscape, and sulfurous gas vents opened across the mountains. Beneath the surface, an immense mass of molten rock surged upward, straining against the crust. The clock ticked toward the end of the slumber for a giant. Toba. This was no ordinary volcano. Toba had erupted 3 times in the past million years, but this time it would become something far greater, a supervolcano. When it finally exploded, the devastation was beyond imagination. From a crater nearly 100 kilometers long, vast columns of ash and rock shot into the atmosphere. Over 14 days, Toba released 3,000 cubic kilometers of debris, 1,000 times more than Mount St. Helens in 1980. This was the largest eruption Earth had seen in at least 25 million years. The fallout was catastrophic. Ash blanketed an area half the size of Europe, while soot and smoke hung in the upper atmosphere, blotting out the sun. The planet plunged into a volcanic winter, with global temperatures dropping by as much as 10 degrees Celsius. Ash fell like rain, and drought gripped the tropics for centuries, maybe even 1,000 years. The impact stretched across the globe, reaching as far as Africa, where our ancestors struggled to survive. Crops failed, food supplies dwindled, and populations plummeted. Some scientists believe that the Toba eruption brought humanity to the brink of extinction, reducing our species to just a few thousand individuals. It was a defining moment, a testament to both Earth's destructive power and humanity's resilience. But what creates such fury beneath the Earth's surface? To find the answer, we must go back to the planet's fiery origins 4.5 billion years ago. In the chaos of the early solar system, dust and rock collided under the pull of gravity, generating immense heat. These collisions forged a molten young Earth. While its surface eventually cooled, its interior remained hot, a furnace fueled by the radioactive decay of elements deep within. That heat still escapes today, finding release through volcanoes, especially along the infamous Ring of Fire, a volatile region circling the Pacific Ocean. Here, massive tectonic plates collide, pull apart, and plunge beneath one another, creating the perfect conditions for volcanic eruptions. Heat from the planet's core rises through the mantle, a vast, semi-solid layer beneath the crust, punching through where the surface is weakest, beneath the oceans. This is the engine driving Earth's most extreme events. Supervolcanoes like Toba remind us of the sheer power locked within our planet. Power that has shaped life and reshaped it time and time again. These eruptions are a window into Earth's restless nature, a force of destruction and renewal that we are only beginning to understand. And as we study these giants, we're reminded that Earth's story is far from over. Its systems may be delicate, but they are resilient, adapting and evolving through cycles of creation and catastrophe. The question remains, will we learn to live in harmony with this dynamic planet? Or will we push it beyond its limits? Only time will tell. Beneath the Earth's crust lies a secret, a volatile force of creation and destruction, and its key ingredient is as simple as it is powerful. Water. When water seeps deep into the ground, it interacts with certain rocks, making them melt more easily. This process creates a molten reservoir of magma, the fiery heart of volcanoes. In the case of Toba, this chain of events spiraled into one of the most extreme eruptions Earth has ever witnessed. As molten rock and debris were ejected violently into the atmosphere, Toba's entire volcanic mountain range collapsed, leaving behind a colossal cauldron-shaped basin. This was a reminder of how water and heat, two of Earth's most fundamental forces, can reshape the planet in ways both spectacular and terrifying. Yet, Earth isn't alone in this volcanic drama. Welcome to Triton, Neptune's frozen moon. With surface temperatures plunging to -235 degrees Celsius, this icy world is no place for lava. Instead, its volcanoes erupt with water ice, painting the landscape with frozen geysers. These super geysers propel liquid nitrogen at nearly 700 kilometers per hour, shooting it up to 8 kilometers above the surface. Elsewhere in the solar system, Io, a moon of Jupiter, boasts volcanic activity on an even more extreme scale. Its eruptions send plumes of gas 500 kilometers above the surface, higher than the orbit of the International Space Station. This volcanic frenzy is powered by Jupiter's immense gravitational pull, which tugs at Io's core, generating intense heat. One of its most remarkable features is Loki, the largest volcano in the solar system, thought to have formed when an ancient impact shattered Io's thin crust. Volcanic activity isn't limited to Triton and Io. It has left its mark on Mars, Venus, and even our own moon. But Earth carries the deepest scars, reminders of a planet constantly remaking itself. The most devastating volcanic event in Earth's history erupted in what is now Siberian Russia, 250 million years ago. During this time, all of Earth's land masses were fused into a single supercontinent called Pangaea, marking the end of the Permian period. Life on Earth was thriving. Amphibians and early reptiles flourished. Forests and swamps teemed with insects, and coral reefs brimmed with marine biodiversity. Then, in what seemed like an instant on the geological timeline, it all came crashing down. The event known as the Great Dying wiped out 70% of land species and 90% of marine species. Entire ecosystems collapsed as the planet faced a mysterious and catastrophic blight. Scientists believe the culprit was a massive plume of magma that surged to the surface. Unlike other eruptions that dissipate their energy over time, this plume erupted as a single sprawling supervolcano. The scale of destruction was unimaginable. These eruptions released lava 1,000 times greater than Toba, flooding the atmosphere with carbon dioxide and methane. Global temperatures soared. The oceans turned acidic, and oxygen levels plummeted, leaving marine life gasping for survival. Earth belched deadly toxins, including high levels of mercury, into the environment. For hundreds of thousands of years, life hung by a thread. Such catastrophic eruptions are rare, but could one happen again? The answer lies closer than you think. Beneath Yellowstone National Park in Wyoming sleeps one of the world's largest active volcanoes. Its legacy is written across the landscape. The Yellowstone River carves through volcanic rock softened by the heat below, while geysers like Old Faithful erupt with clockwork precision, spewing jets of boiling water into the air. These spectacles are fueled by an immense plume of magma deep underground, over 100 kilometers wide and 400 kilometers deep. Yellowstone's history is marked by powerful eruptions, each following the same pattern as Toba: sudden magma release, land collapse, and the rise of a supervolcano. Though it hasn't erupted for over 600,000 years, scientists know it's not a question of if, but when. They keep watch for telltale signs: earthquakes, rising heat, and the restless movements of a planet under pressure. For now, Yellowstone remains a sleeping giant, but its geysers serve as a reminder of the forces simmering below. When the next supervolcano erupts, it will reshape life on Earth in ways we cannot yet imagine. These rare but devastating events are a testament to Earth's power to create and destroy, and they challenge us to understand our planet's volatile rhythms. Earth may be our home, but its story is one of constant transformation, a delicate balance of forces that can nurture life one moment and threaten its very existence the next. The next chapter in this tale is yet to be written, but one thing is certain: the fury of the Earth remains, ever present, beneath our feet. The space race wasn't just a competition, it was a clash of ideologies, fueled by a desire to prove technological and scientific superiority. The Soviet Union and the United States pushed the boundaries of human innovation, achieving remarkable advances in computers, satellites, and rocketry. But perhaps the most enduring legacy of this era wasn't a machine. It was a collection of rocks brought back from the moon, holding the secrets to our planet's early history and the moon's mysterious origins. For thousands of years, the moon has been a source of wonder, the brightest object in the night sky. It has inspired myths, set the rhythms of life, and even stabilized Earth's rotation, creating the tides that shaped ocean currents and influenced our climate. Yet, behind its brilliant glow lies one of science's most enduring mysteries. Where did the moon come from? At the dawn of the space age, scientists debated three theories. Some thought the moon was once part of Earth, flung off by the planet's rapid spin. Others believed it was a wandering object, captured by Earth's gravity. A third idea suggested that Earth and the moon formed together from the same primordial cloud of dust and gas. To find the answer, both the United States and the Soviet Union launched missions to photograph, study, and even crash probes onto the moon's surface. But to truly solve the puzzle, we needed to bring a piece of the moon back to Earth. The race to the moon began with the Soviet Union's launch of Sputnik in 1957, the first artificial satellite to orbit Earth. Its success startled the world and spurred the United States to action, leading to the creation of NASA. The Soviets quickly followed up with Sputnik 2, carrying the first living creature into space, a dog named Laika, and later sent Yuri Gagarin, the first human, into orbit in 1961. The United States struggled to keep pace until President John F. Kennedy set an ambitious goal: land a man on the moon before the decade was out. Achieving this goal was no easy task. The United States developed the Gemini program to master the skills needed for a lunar mission, but progress was slow and riddled with setbacks. Meanwhile, the Soviet Union worked on its N-1 rocket, a massive and complex vehicle with 30 engines that needed to fire perfectly in sync, a feat that proved insurmountable. By the late 1960s, both nations were locked in a high-stakes race to make history. The Americans placed their faith in the Saturn V, a towering rocket designed to carry the Apollo missions to the moon. In 1968, Apollo 8 successfully orbited the moon and returned, proving the mission was within reach. In July 1969, the Soviets launched Luna 15, an unmanned probe designed to collect lunar samples and return them to Earth just days later. The United States launched Apollo 11, carrying astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins. On July 20th, 1969, Armstrong and Aldrin began their descent to the lunar surface aboard the Eagle. The landing was fraught with tension. Alarms blared, fuel ran low, and boulders littered the landing zone. Taking manual control, Armstrong guided the craft to safety, uttering the famous words, "Houston, Tranquility Base. Here, the Eagle has landed." Moments later, Armstrong stepped onto the moon, calling it a giant leap for mankind. Meanwhile, Luna 15 attempted its descent, but lost communication and likely crashed into a mountainside, signaling the end of the Soviet effort to claim the moon. The triumph of Apollo 11 wasn't just about landing, it was about what the astronauts brought back: lunar rocks and soil samples held clues to the moon's ancient history, frozen in time. Scientists noticed strange concentric rings around large craters, hinting that the moon's surface was once a vast ocean of magma. The light rocks scattered across the surface suggested denser materials had sunk into the moon's interior. Even more striking, the rocks shared chemical similarities with Earth, including identical oxygen isotopes. This discovery sparked a groundbreaking theory. According to the giant impact hypothesis, early in the solar system's history, a Mars-sized body named Theia collided with Earth. The impact sent debris from both bodies into orbit, eventually coalescing into the moon. This cataclysmic event explains the moon's lighter density and lack of water. As the moon cooled, its magma ocean solidified into a crust, but it wasn't out of danger yet. The early solar system was a chaotic place, with massive collisions shaping planets and moons alike. The moon's surface was scarred by powerful impacts, some so intense they melted the surface, creating vast volcanic plains known as Maria. These smooth, dark regions, covering 1/6 of the moon's surface, were formed 3 to 4 billion years ago, during a period of intense bombardment. The Apollo missions gave humanity more than rocks. They gave us a window into the violent history of our solar system. They revealed the moon not as a static, lifeless object, but as a dynamic partner in Earth's story. As we look to the future, the lessons of the moon remind us of our planet's own turbulent past and inspire us to continue exploring the mysteries of the cosmos. Recent discoveries suggest the moon's lopsided appearance, its dark lava basins on the near side and highlands on the far side, might hold clues to a dramatic event from its early history. One theory proposes that a smaller celestial body formed alongside the moon during its creation and eventually collided with it. This violent merger reshaped the moon's interior, pushing molten magma to the near side, creating the lava plains we see today, and adding an extra layer of crust to the far side. The Apollo astronauts paved the way for uncovering these mysteries by deploying seismographs on the lunar surface, which recorded moonquakes and provided insight into its interior building. On this foundation, scientists launched the Grail mission, using 2 spacecraft flying in tandem around the moon. By precisely measuring changes in the distance between the spacecraft, researchers mapped the moon's gravity field in astonishing detail. What they found was surprising. Pockets of intense gravity, called mascons, linked to ancient impact sites like Mare Orientale, highlighting the powerful role impacts played in shaping the moon's surface and core. These collisions also left behind an unexpected gift: water ice. In 2009, NASA's LCROSS mission deliberately crashed into a crater near the moon's South Pole instruments. On a trailing probe detected a plume of material rising from the impact. Within that plume, scientists found traces of water ice, making up 5.6% of the crater floor. But that's just the tip of the iceberg. Data from the Lunar Reconnaissance Orbiter suggests that hydrogen and possibly water ice may be widespread across the moon, even outside polar regions. Meanwhile, new techniques applied to the Apollo rock samples revealed the presence of hydroxyl, a molecule similar to water. Scientists now estimate that if all the water trapped inside the moon were released, it could cover the entire surface in a 1-meter-deep layer. This discovery reshapes our understanding of the moon's relationship with Earth. It reveals a bond that stretches back billions of years to their shared origins in a colossal collision. Yet, despite these breakthroughs, we've only begun to explore the moon's hidden depths. The quest to understand the moon, once a battleground of Cold War rivalry, has entered a new phase. Nations like the United States, Russia, China, India, and Japan are planning new missions, some aimed at uncovering more lunar secrets, others focused on mining valuable metals and minerals. Private companies are also entering the race, dreaming of lunar bases and commercial opportunities. As humanity prepares to return to the moon, each mission brings us closer to answering fundamental questions about its origins and its role in shaping our planet. The more we learn about the moon, the more we uncover about Earth's own story. A tale of creation, destruction, and the enduring partnership between our world and its only natural satellite. Water, the elixir of life, isn't confined to Earth. It's scattered across our solar system, hiding in unexpected places and telling stories of distant worlds. At the outermost edges of the solar system, Pluto and its moon, Charon, are icy relics from the formation of the planets. Their surfaces are coated in frozen methane and water ice, remnants of an ancient cosmic past. Closer to the Sun, the icy giants Neptune and Uranus are veiled in methane clouds, but deep inside, charged particles churn in liquid water layers, creating magnetic fields. These alien oceans, more akin to acidic batteries than earthly seas, hold secrets waiting to be uncovered. Within Saturn's rings, countless icy fragments swirl in orbit, while its moon Enceladus glistens with an icy crust that makes it one of the brightest objects in the solar system. The Cassini spacecraft captured breathtaking images of water jets erupting from Enceladus's south pole, hinting at a vast underground ocean hidden beneath the frozen surface. Could this ocean harbor microbial life, shielded from the harshness of space by its icy shell? Then there's Jupiter. The solar system's giant water is sparse in its thick atmosphere, but it plays a crucial role in fueling its colossal storms, like the iconic Great Red Spot, where water vapor rises and falls in cycles eerily similar to Earth's thunderstorms. Beyond Jupiter's turbulent skies lies Europa, a moon with a smooth, icy surface marked by grooves and ridges. These patterns suggest a subsurface ocean of liquid water, warmed by the constant gravitational tug-of-war with Jupiter. If life exists beneath Europa's frozen crust, it might echo the first primitive life forms on Earth. Even small, seemingly barren objects carry traces of water. Asteroids, often dismissed as rocky remnants, hold minute amounts of frozen water. On Mercury, the Sun's closest planet, ice is tucked away in craters near the poles, permanently shielded from solar heat. The Moon, too, holds water in shadowed craters at its poles, and possibly deep within its rocky interior, as revealed by Apollo mission samples. Mars, once a planet of flowing rivers and lakes, now stands as a stark reminder of water's fragility. Ancient riverbeds snake across its surface, evidence of a wetter past today. Mars is a cold, dry desert, with fierce dust storms scouring the landscape and frozen carbon dioxide frosting the ground in winter. If water still exists there, it's likely trapped below the surface, locked within rocks. On the other hand, Venus, Earth's sister in size and composition, is a vision of extremes. Its thick clouds of sulfuric acid and runaway greenhouse effect have turned it into a furnace. With surface temperatures hotter than Mercury, any water Venus once had was stripped away by solar winds, its hydrogen and oxygen escaping into the void of space. So why is Earth so different? Our planet is wrapped in a magnetic field, generated deep within its molten core, acting as a shield against the solar wind. This protection has allowed Earth's water to persist and cycle for billions of years. Today, water dominates our world, flowing in rivers, filling oceans, and drifting as vapor in the atmosphere. It shapes our landscapes, fuels life, and regulates the planet's climate. At the heart of Earth's balance is a trace gas, carbon dioxide, CO2. Acting as the planet's thermostat, CO2 traps just enough heat to maintain a stable climate, allowing liquid water to thrive. But this balance wasn't always present. In its fiery youth, Earth's atmosphere was thick with CO2, released by violent volcanic eruptions. Over time, chemical reactions between rocks and water drew CO2 out of the air and into the oceans. There, life began to take root. Primitive organisms evolved, using sunlight to convert CO2 into oxygen through photosynthesis, forever transforming the planet. Water is essential, but it's not the only ingredient for a life-supporting planet. The ability to cycle carbon, regulate climate, and maintain liquid water sets Earth apart. This delicate balance might be the rarest quality any alien world must achieve to be truly Earth-like. A harmony that makes our blue planet a cosmic masterpiece. For millennia, humanity has sought to understand its home, a planet teeming with water and life. But now, we're gazing outward, equipped with advanced tools, searching the vastness of space for planets like ours. Could there be other water worlds out there, perhaps teeming with life, primitive or intelligent? Hints have emerged from the study of distant stars, like Kepler-62, a star located 1,200 light-years away. Using the Kepler Space Telescope, scientists discovered two Earth-sized planets orbiting within the star's habitable zone, the region where temperatures might allow liquid water to exist. But what lies on their surfaces? Are they Earth-like, with protective magnetic fields and vast oceans? Or have they succumbed to a runaway greenhouse effect, like Venus, a searing furnace with a dense atmosphere of carbon dioxide and clouds of sulfuric acid? The search for life among the stars is a quest to find a second oasis in the cosmos. We're looking for the unique fingerprints of an Earth-like world, one that might echo the delicate balance of conditions that sustain life here. What once seemed like science fiction, traveling to other worlds and encountering alien landscapes, is now becoming reality. The space age has unlocked a new era of discovery, and each year, astronomers detect more planets orbiting distant stars. Some are strange and hostile with searing heat or crushing pressure, but a few seem tantalizingly familiar, sparking hope that they might harbor the conditions needed for life. This journey began in 1995 when astronomers discovered the first confirmed planet outside our solar system, orbiting a star called 51 Pegasi, about 50 light-years away. This planet, known as a hot Jupiter, defied expectations. It's over 100 times the size of Earth but orbits incredibly close to its star, completing a full revolution in just 4 Earth days. With surface temperatures reaching 1,300 degrees Celsius, this discovery upended our understanding of how planetary systems form and evolve. In our own solar system, planets formed billions of years ago in a spinning disk of gas and dust. The rocky worlds like Earth and Mars took shape near the Sun, while gas giants like Jupiter and Saturn formed farther out. Yet 51 Pegasi b's proximity to its star suggests a different story. Perhaps it formed farther away and later migrated inward, reshaping the rules of planetary science. Astronomers found 51 Pegasi b using the wobble method, which detects the gravitational pull a planet exerts on its star, causing the star to move ever so slightly. By measuring shifts in the star's light spectrum, scientists can infer the presence of an orbiting planet. Modern instruments are so precise they can detect shifts as small as 1 meter per second, the speed of a casual walk. Another technique, the transit method, measures the tiny dimming of a star's light when a planet passes in front of it. In 1999, this method revealed the planet HD 209458b, another hot Jupiter. When it transited its star, the star's brightness dipped by just 1%, but this was enough to confirm the planet's existence. Observations later showed that this planet is puffier and less dense than any in our solar system, challenging our understanding of planetary atmospheres. These methods have opened the door to even more astonishing discoveries. By analyzing the light that filters through a planet's atmosphere during a transit, scientists can identify the chemical composition of that atmosphere. For HD 209458b, the Hubble and Spitzer space telescopes detected sodium, methane, water vapor, and possibly carbon dioxide, molecules that, under the right conditions, could signal the presence of life. This capability has profound implications. The same techniques could one day detect biosignatures, like oxygen or methane, on rocky, Earth-like planets. But life needs more than just the right chemicals. It requires a stable source of energy, such as a star, and liquid water. The universal solvent planets in the habitable zone, neither too hot nor too cold, are prime targets in this cosmic hunt. With billions of stars in the Milky Way, the possibilities seem endless, but not all stars are suitable. Massive supergiants, for example, burn brightly but live short lives, leaving little time for life to take hold. Instead, scientists focus on smaller, longer-lived stars like our Sun, hoping to find planets with solid surfaces and conditions where water can flow freely. Every new discovery brings us closer to answering the age-old question: are we alone? Somewhere in the vast tapestry of the galaxy, there may be another world like ours, a planet where water flows, life thrives, and the story of existence unfolds. Each star we study, each exoplanet we find, brings us one step closer to understanding not just the universe, but ourselves. Not every star in the galaxy can cradle life. Supergiants, for instance, shine with intense brilliance, but burn out in a cosmic blink of an eye. Their lifespans are too short for life to gain a foothold, and when they die in violent supernova explosions, any surrounding planets are obliterated. Binary or triple star systems, which make up over half the stars in the galaxy, are also problematic. The constant gravitational tug-of-war between multiple stars would wreak havoc on a planet's orbit, making conditions far too chaotic for life to develop. Red dwarfs, however, hold promise. These stars are smaller, cooler, and dimmer than our Sun, but they have a significant advantage: longevity. Red dwarfs live for billions of years, offering plenty of time for life to evolve. In 2009, astronomers discovered Coro 7b, the first rocky super-Earth orbiting a red dwarf. But this world is no haven. It zips around its star in just 20 hours, with surface temperatures of 2,000 degrees Celsius, likely covered in molten rock. Most super-Earths found so far share a similar fate, close to their stars and blisteringly hot. But not all hope is lost. Consider Gliese 581, a red dwarf just 20 light-years away. This star hosts a fascinating planetary system, including Planet D, which sits at the cold outer edge of the habitable zone. With only 30% of the sunlight Earth receives, it may resemble a frozen, larger version of Mars. However, what if it had a thick atmosphere to trap heat, a stabilizing moon, and a protective magnetic field? These features could make it surprisingly Earth-like. Future technology may allow astronomers to detect its atmospheric composition, searching for methane, water vapor, or other chemicals tied to life. Our ability to hunt for Earth-like planets has skyrocketed thanks to the Kepler Space Telescope. Launched in 2009, designed to pinpoint tiny dips in starlight caused by planetary transits, Kepler has already revolutionized our understanding of exoplanets. It has identified a plethora of solar systems that defy expectations. Kepler 11, for instance, packs 6 planets larger than Earth into tight orbits, closer to their star than Venus is to the Sun. Kepler 20 hosts Earth-sized planets that orbit even closer than Mercury. The discoveries become even stranger with systems like Kepler 47, a binary star system with 2 planets. One of these planets lies in the habitable zone, but it's a gas giant, a distant cousin of Neptune, rather than a rocky world like Earth. These findings raise tantalizing questions. Are Earth-like planets rare jewels in the universe? Or are they more common than we ever imagined? As we continue to push the limits of technology, the answers are slowly coming into view. Advanced telescopes, coupled with cutting-edge computing, are enabling astronomers to uncover an unprecedented diversity of worlds. But even if Earth-like planets are commonplace, one thing remains certain: our world is unique, a delicate oasis in the vast, silent expanse of the cosmos. Looking up at the night sky, the universe seems infinite, stretching endlessly in all directions. For billions of years, it has evolved, and it will continue for billions more after we are gone. In this grand cosmic timeline, our existence is fleeting, a mere breath in the life of the universe. Yet, through our curiosity and determination, we strive to uncover our place in this immense and awe-inspiring story. When we gaze at the stars, their calm, unwavering presence gives the illusion of permanence. But hidden beneath their serene glow is a universe of chaos, where stars live dramatic lives and die explosive deaths. These final moments, especially for giant stars, are among the most breathtaking and transformative events in the cosmos. At the end of its life, a giant star becomes a tempest of unimaginable power. On its surface, superheated gases churn, creating tsunamis thousands of kilometers high. Loops of electrified gas, larger than planets, arc out into its atmosphere. Deep within, the star's core, once a crucible of nuclear fusion, can no longer sustain the immense forces pushing against gravity. It collapses, triggering a supernova, a cataclysm so powerful it outshines entire galaxies for a brief moment in time. What follows is both destruction and renewal. The explosion scatters the star's core elements, carbon, oxygen, iron, and more, across space, sowing the seeds for new stars, planets, and even life. These elements, forged in the heart of dying stars, are the building blocks of everything we know, including ourselves. Without supernovas, the universe would lack the essential materials for life. Throughout history, humans have occasionally witnessed these stellar deaths. In 1054, a supernova lit up the sky so brightly that it was visible during the day, recorded by stargazers in North America, China, and the Middle East centuries later. Astronomers like Tycho Brahe and Johannes Kepler studied similar events, challenging the belief that the heavens were unchanging. These supernovas not only reshaped our understanding of the cosmos, but also hinted at the immense forces shaping the universe. Modern astronomers, equipped with advanced telescopes and instruments, have taken the study of dying stars to new heights. Using the electromagnetic spectrum, they detect everything from low-energy radio waves emitted by distant objects to high-energy gamma rays produced during explosive cosmic events. These observations allow scientists to peer into the heart of stellar death and uncover the secrets of the universe's violent evolution. Our Sun, a modest star, provides a glimpse into this process deep in its core. Nuclear fusion converts hydrogen into helium, releasing energy that pushes outward and counteracts the force of gravity. This delicate balance allows the Sun to shine steadily for billions of years. But for massive stars, this balance is short-lived. They burn through their fuel rapidly, their cores becoming dense with heavy elements, like iron. Once fusion ceases, gravity takes over, and the star collapses in on itself, leading to a spectacular supernova. But these explosions leave behind more than debris. Shock waves from the blast can compress nearby gas clouds, sparking the birth of new stars. In places like the Orion Nebula, we can see this cycle in action, as dense clouds of gas and dust form stellar nurseries. Here, stars and planetary systems are born, continuing the cosmic cycle of death and renewal. Not all remnants of a supernova scatter into the cosmos. Some collapse into exotic objects, like neutron stars. These incredibly dense cores are so compact that a teaspoon of neutron star material would weigh billions of tons. Some neutron stars spin at incredible speeds, emitting beams of radiation as pulsars, like cosmic lighthouses sweeping through the galaxy. One such pulsar lies at the heart of the Crab Nebula, a remnant of the supernova observed in 1054. Its waves of radiation have carved intricate patterns into the surrounding gas, a vivid reminder of the power locked within these dying stars. For the most massive stars, their deaths can give rise to the universe's most enigmatic phenomenon: the black hole. First theorized by Albert Einstein, a black hole forms when gravity becomes so overwhelming that it crushes the star's core to an infinitely small point. Even light cannot escape its pull, making black holes invisible and mysterious. What was once dismissed as a theoretical impossibility now stands as a cornerstone of modern astrophysics. As black holes form, they rewrite the rules of reality, warping space and time around them. They are the ultimate endgame of stellar evolution, where gravity claims its final, absolute victory. Yet, even in their terrifying finality, black holes are not mere destroyers. They influence their surroundings, shaping galaxies and fueling some of the most energetic phenomena in the universe. The death of a star is not just an end, but a beginning, a process that seeds the cosmos with the elements of life and sets the stage for the next generation of stars and worlds. It reminds us that even in destruction, the universe finds a way to create anew, an eternal cycle of life, death, and rebirth played out on the grandest of scales. Black holes are cosmic enigmas, mysterious entities that warp the very fabric of space and time. They're invisible, emitting no light, but their existence is betrayed by their influence on the universe around them. By observing flashes of gamma radiation and the spectacular jets of matter they eject, astronomers have unraveled their secrets, revealing how black holes are both destructive and creative forces. One groundbreaking discovery came when telescopes caught a gamma-ray burst near the center of the Milky Way. This wasn't just a fleeting flash, it marked the presence of a stellar black hole, a voracious predator siphoning gas from a neighboring star. As this gas spiraled into the black hole, it formed an accretion disk, a swirling maelstrom of material that heated up and generated immense magnetic fields. These fields directed some of the infalling gas outward in the form of jets of high-energy particles, which streaked through space at nearly the speed of light. The black hole in question, GRJ 1655-40, isn't just remarkable for its ravenous appetite. It's also on the move, hurtling through space at an incredible 400,000 kilometers per hour. This rogue black hole likely gained its speed during the supernova explosion that birthed it. Ejected like a cannonball, it stands as a testament to the explosive power of stellar death. Yet black holes are far more than cosmic vacuum cleaners. They are architects of the universe, their gravitational pull shaping the formation and evolution of galaxies. In the early universe, when the first stars formed, some massive ones ended their short, luminous lives in catastrophic collapses, leaving behind primordial black holes. Over billions of years, these black holes merged with others and consumed vast amounts of gas and stars, growing into supermassive black holes, some with masses billions of times that of the Sun. These supermassive black holes don't just sit at the centers of galaxies, they regulate their growth. By consuming matter and ejecting energy in jets, they heat surrounding gas, preventing it from cooling and forming new stars. This feedback process slows the central galaxy's growth, while allowing smaller galaxies to develop on the periphery. In essence, black holes are both the gardeners and gatekeepers of the cosmos. Consider the Hydra a galaxy cluster, an awe-inspiring example of this phenomenon. Observations from the Chandra X-ray Observatory reveal vast cavities glowing in X-ray light, carved by powerful jets from a central supermassive black hole. These jets carry heavy elements, forged in the fiery depths of stars, into distant regions of the universe. This dispersal of elements seeds the cosmos, enabling the formation of new stars, planets, and even the building blocks of life. Supermassive black holes are now known to reside in nearly every large galaxy, including our own Milky Way, where Sagittarius AE reigns at the center across the universe. Telescopes frequently capture these titanic forces in action, their jets blazing like cosmic lighthouses. The connection between black holes and life on Earth is profound. The very elements in our bodies, carbon, oxygen, iron, were forged in the nuclear furnaces of stars and scattered by supernovae, often with black holes playing pivotal roles. These distant, violent events are the foundation of everything we know. Our exploration of the cosmos highlights this link. The Voyager spacecraft, launched in 1977, have ventured to the edge of the solar system, tens of billions of kilometers from Earth, traveling at 16 kilometers per second. Voyager 2 will pass near the star Sirius, but not for another 290,000 years. Even at these extraordinary distances, the echoes of star life cycles guide us, reminding us of the intricate dance between creation and destruction. Black holes, once dismissed as theoretical curiosities, are now understood as central players in the cosmic story. They destroy, create, and reshape the universe in ways that challenge our understanding of physics and existence itself. These mysterious giants remind us that even in destruction, there is the potential for rebirth and transformation, a cosmic cycle as old as time. The foundations of science laid by the ancient Greeks, pioneers like Aristotle and Ptolemy, were monumental for their time. But if they could glimpse the discoveries of modern astronomy, they would be astounded. The stars and planets they thought to be divine are now understood as mere grains in a vast cosmic scaffold of matter and energy stretching into the infinite. For centuries, Aristotle's model of a cosmos with Earth at its center held sway. It wasn't until the 16th century that Nicholas Copernicus presented a revolutionary idea. Earth and the other planets revolve around the sun. With this, he also revealed that planets follow specific orbits and suggested something even more radical. The stars we see are unimaginably far beyond our solar system. This paradigm shift expanded further in 1609, when Galileo Galilei turned the first astronomical telescope toward the night sky. What he saw redefined our understanding of the heavens. The Milky Way, which seemed like a misty band in the sky, was actually composed of countless stars. Galileo had opened humanity's eyes to the true scale of the universe. Over the centuries, astronomers discovered that the Milky Way wasn't just a collection of stars, but a vast spinning disk of gas and stars. For a time, it was believed to be the entirety of the universe, a massive yet self-contained island of light and matter. Then came the observations that changed everything. Using a 100-inch telescope at Mount Wilson in California, Edwin Hubble and his assistant Milton Humason studied faint, blurry spots in the sky called nebulae. To their astonishment, these nebulae were not clouds of gas within our galaxy. They were other galaxies, each teeming with billions of stars and located far beyond the Milky Way. Even more incredible, they found that these galaxies were moving away from us, and the farther away they were, the faster they receded. The universe, they realized, was expanding. This discovery transformed our understanding of space and time. Astronomers now knew that peering deep into space meant looking back in time, since light from distant galaxies takes millions or even billions of years to reach us. To unravel the mysteries of the cosmos, larger and more powerful telescopes were built, reaching deeper into the universe's history. What they revealed was a dynamic, chaotic universe shaped by violent explosions, swirling shock waves, and the collapse of massive stars into black holes. By the 20th century, the universe's story had a dramatic beginning: the Big Bang. This theory wasn't just speculation, it rested on solid evidence. First, the universe is expanding. and tracing that expansion backward points to a single origin. Second, the abundance of light elements, such as hydrogen and helium, fits the conditions of the universe's earliest moments. Third, faint cosmic microwave radiation, a relic of the young universe, bathes the cosmos. Finally, the model provided a timeline for the formation of stars, galaxies, and the large-scale structures we see today. Yet, as groundbreaking as the Big Bang model was, it raised new questions. Precision measurements from the Hubble Space Telescope revealed that the universe is approximately 13.7 billion years old. Even more astonishingly, galaxies at the edge of the observable universe are roughly 46 billion light-years away due to the universe's expansion. But what lies beyond them? Does the universe have an edge? Or is it infinite? Astronomers were also puzzled by a curious uniformity in the cosmos. No matter where they looked, the distribution of galaxies, the density of matter, and even the temperature of the universe appeared remarkably consistent. How could such an immense and expanding universe be so evenly balanced? The answer came in the form of a groundbreaking idea: cosmic inflation. This theory proposed that, in a fraction of a second after the Big Bang, the universe underwent an unimaginable burst of expansion. During this brief moment, the universe grew exponentially, smoothing out irregularities and creating the seeds for all the cosmic structures we see today. In 1990, the Hubble Space Telescope began capturing breathtaking images of distant galaxies, while another mission, COBE, provided crucial evidence for inflation. COBE detected faint microwaves from the early universe and found subtle variations, tiny, hot, and cold spots in the cosmic background radiation. These were the imprints of the universe's earliest structure. Subsequent missions, like WMAP and Planck, sharpened these observations. They revealed a cosmos that was smooth on the largest scales, but filled with subtle variations that would grow into galaxies, stars, and planets. These findings confirmed that inflation was the missing piece of the Big Bang puzzle, explaining not just the size and uniformity of the universe, but also its incredible complexity. Today, astronomers use powerful telescopes and supercomputers to simulate how the universe evolved from these early seeds. Starting from tiny fluctuations in density, gravity gradually amplified these ripples, forming stars, galaxies, and colossal clusters of matter. These simulations bring us closer to understanding how the cosmos grew into the grand and intricate tapestry we see today. As we continue to probe the heavens, we are left with profound questions. How far does the universe truly extend? Is there a boundary, or does it go on forever? And in the midst of this vast expanse, what role does our tiny blue planet play in the cosmic story? Each discovery adds another layer to this narrative, bringing us closer to unraveling the ultimate mysteries of existence. Astronomers have embarked on an extraordinary journey to trace the evolution of our universe from its earliest moments. With the aid of sophisticated computer-controlled telescopes and international collaborations, they've crafted detailed three-dimensional maps of the visible cosmos, revealing its astonishing structure. Our map begins close to home in the local group, a collection of about 20 galaxies bound together by gravity. Moving outward, we encounter the Virgo supercluster, a bustling intergalactic metropolis located roughly 50 million light-years away. Beyond Virgo lies a grand tapestry of galaxies arranged in vast arcs and walls, stretching across unimaginable distances. At this scale, the universe takes on the appearance of a cosmic web. with immense filaments of galaxies acting as its threads and vast empty voids in between. To explain the origins of these structures, scientists proposed a revolutionary concept called cosmic inflation, a theory that transformed our understanding of the early universe. The inflation model is built on the discovery that energy can spontaneously emerge from the vacuum of space, creating fleeting pairs of matter and antimatter particles. These energy fields, in an instant, tipped into a high-energy state, causing the universe to undergo a rapid and explosive expansion, growing exponentially in size in a fraction of a second. This inflation wasn't smooth. Tiny fluctuations in the primordial energy left ripples, like waves spreading across a pond. Over time, these ripples became denser regions of matter, which gravity amplified into the stars, galaxies, and galaxy clusters we see today. To connect these early ripples to the vast structures surrounding us now, astronomers turned to supercomputers to simulate the universe's evolution. By rewinding cosmic history to a time when the universe was just 10% of its current age, these simulations reveal how matter coalesced into dense regions, forming stars, galaxies, and immense galactic clusters. But even the most advanced simulations capture only a fraction of the visible universe. The full story of inflation suggests a universe far more vast than what we can observe. According to the theory, the cosmos expanded from a size smaller than an atom to a scale we can hardly imagine, all in less than a blink of an eye. Since then, it has continued to grow, now believed to be 10 billion trillion times larger than the observable universe. To put this into perspective, if the observable universe were an atom, the whole universe would be as vast in comparison as the observable universe is to the atom itself. Yet, as incomprehensibly vast as this is, it might not be the ultimate limit. Just a few centuries ago, Galileo revealed that our Sun is one star among countless others. A few decades ago, Edwin Hubble showed that the Milky Way is merely one galaxy in a boundless sea of others. Today, we've uncovered clusters of galaxies, colossal walls of matter, and a cosmic web that spans billions of light years. Cosmic inflation has further expanded our horizons. Some versions of the theory suggest that our universe is just one of many, part of a multiverse, where other universes rise and expand like bubbles in an infinite ocean. This idea challenges us to rethink our place in the cosmos. Does the realization of such vastness make Earth feel small and insignificant, relegated to a forgotten corner of existence? Or does humanity's ability to uncover these truths, to map the unobservable, and grapple with infinite possibilities, elevate our significance in the grand story of the cosmos? Space, the ultimate frontier. It's a place of endless possibilities and unfathomable mysteries that have captivated humanity for centuries. From the vast, silent void stretching across the cosmos to the very origins of time itself, the universe beckons us to explore its secrets. Together, let's embark on a journey to unravel these enigmas, reflect on its incredible past, and wonder about the destiny of the universe. We'll travel back to the very beginning, witness the grand story of its evolution, and peer forward into the distant future. Along the way, we'll question the boundaries of existence and whether there's truly an edge to everything we know. The universe, in all its enormity, holds a profound mystery that defies our understanding. It ignites our imagination and challenges everything we think we know. That mystery is the question: what lies beyond the universe? Your seat. As we venture deeper into the cosmos, we quickly realize that our perspective is limited. Our observable universe acts like a prison, restricting what we can see and know. Beyond this boundary lies an unknown realm, a cosmic curtain shrouding the secrets of existence. Trying to grasp the idea of beyond feels almost impossible. How do you imagine something you can't perceive? Yet, this question drives us to push the limits of human thought, inspiring a relentless search for answers. Everything we've ever seen, from the objects in a room to galaxies visible only through giant telescopes, is part of the observable universe. This observable portion of the cosmos has a radius of 46.5 billion light-years. But here's the twist. The universe itself is only 13.8 billion years old. How does that even make sense? It all comes down to the universe's expansion. As the universe stretches, the areas emitting light keep moving farther away, so we observe them at great distances. This 46.5 billion light-year radius forms the boundary of what we can see, even though the entire universe might be infinite. What's beyond this limit? Modern science doesn't know. These boundaries, or cosmological horizons, aren't physical walls. Instead, they're determined by light. Think about this. The night sky isn't completely filled with stars. Why? Because light can only travel a certain distance to reach us. It's as though there's an invisible sphere surrounding us, beyond which countless stars and galaxies remain hidden. Scientists call this invisible edge the particle horizon and the event horizon. The two are different, though. The particle horizon marks how far light from the past has traveled to reach us today, while the event horizon is the limit of how far light can travel into the future to reach an observer. Beyond these horizons lies another boundary, the Hubble horizon. Objects beyond this horizon move away so fast, at the speed of light, that their light can never reach us, no matter how much time passes. It's not the universe itself that's limited. It's the light we rely on to see it. Here's a relatable example. Light isn't instantaneous. It takes time to travel, For instance, sunlight takes about 8 minutes to reach Earth, even though the Sun is 94 million miles away. Proxima Centauri, the closest star to us outside our solar system, is 4.2 light-years away. That means its light takes 4.2 years to get here. When we look at the night sky, we're not seeing the present. We're looking into the past. The farther away an object is, the older the image we're seeing. Let's put that into perspective. To update our understanding of an extremely distant object, like the HD-1 galaxy, located 13.4 billion light-years away, we'd need to wait 13.4 billion years to see what it looks like now, assuming nothing blocks the light. If we could study it closely, we might uncover clues about how our own galaxy formed in the early universe. Light, as it turns out, is our cosmic time machine. It's through detecting this ancient light that we've pieced together the Big Bang Theory and much of the universe's history. The universe is vast and mysterious, but light offers us a glimpse into its story, both its origins and its future. While we may never know what lies beyond our observable limits, the pursuit of understanding fuels the human spirit. Each discovery, each piece of ancient light we capture, brings us closer to answering the greatest questions of existence. The journey is far from over, and the cosmos has far more stories to tell. To deepen our understanding of distant cosmic objects, consider the HD-1 galaxy, an incredible 13.4 billion light-years away. Observing it in detail could unlock the story of how our galaxy formed in the early universe. But there's a catch. Light from such objects takes billions of years to reach us, and obstacles like black holes could block the view. This makes light detection an essential tool for studying the universe's evolution. Thanks to this, we've pieced together the Big Bang Theory, a blueprint of how everything we know began. The Big Bang didn't just create the universe, it left behind a profound trace. In the mid-20th century, astronomers Arno Penzias and Robert Wilson stumbled upon this evidence while working with radio telescopes. They picked up a strange, faint signal, seemingly coming from everywhere with the same intensity. It turned out to be the cosmic microwave background radiation, CMB, the remnants of the universe's first light. In the fiery chaos of the Big Bang, atoms couldn't form. The extreme temperatures kept electrons and protons apart, and photons, particles of light, were scattered or absorbed before they could travel far. The universe, at that time, was a dense, glowing fog. Then, 380,000 years after the Big Bang, the universe began to cool. This cooling allowed the first stable atoms to form, turning the cosmos transparent. Light, for the first time, could travel freely across vast distances. That ancient light, now stretched into the microwave spectrum due to the universe's ongoing expansion, is what we detect as CMB. Its faint glow, at a temperature just above absolute zero, 454 degrees Fahrenheit, can be seen in every direction from Earth. Stretching out to a distance of 13.8 billion light-years, the CMB has helped scientists estimate the universe's age. However, this number represents only the limit of what we can observe, not necessarily the universe's full extent. Interestingly, the CMB isn't visible to the naked eye. Over time, as the universe expanded, The wavelengths of this ancient light stretched out, losing energy and slipping into the microwave spectrum. Despite its faintness, the CMB has opened a window into the past, allowing scientists to glimpse the earliest chapters of the universe. Tools like the Large Hadron Collider, LHC, provide further insights, helping us reconstruct the story of how the universe evolved from a singularity to the sprawling cosmos we see today. The CMB's fluctuations reveal a spotted map of the sky. Blue areas on the map indicate regions cooler than average, while orange areas are warmer. These patterns reflect density variations, seeds of the structures that would later grow into stars, galaxies, and clusters. The largest spots, spanning about 1 angular degree in the sky, offer evidence that the universe is flat, not curved. Smaller spots provide a treasure trove of data about the universe's composition and age. One of the most groundbreaking revelations from studying the CMB is the existence of dark matter and dark energy, two mysterious forces that dominate the universe. In 2003, astronomers led by D.N. Spergel determined that dark matter makes up 26.8% of the cosmos, while dark energy accounts for a staggering 68.3%. Ordinary matter, everything we can see and touch, makes up just a tiny fraction of the total. The CMB also revealed that the universe is expanding at a rate of 42 miles per hour per megaparsec, a finding that shapes our understanding of the cosmos's future. Both the CMB and the boundaries of space, known as cosmic horizons, define the limits of what we can observe from Earth. Let's dive into these horizons. The particle horizon is like a bubble marking the farthest distance light from the past has traveled to reach us. Beyond this lies a vast unknown, filled with objects whose light hasn't had enough time to get here. The particle horizon isn't a fixed boundary, though. Over immense spans of time, it shifts outward as light from more distant objects finally reaches us. The more we uncover, the more questions emerge. The CMB and space horizons remind us that our view of the universe is both vast and incomplete. They challenge us to look further, think deeper, and keep pushing the boundaries of human understanding. What lies beyond these limits? We may never fully know, but the quest to find out is what makes the journey so extraordinary. Even as the light of the cosmos continues its seemingly endless journey, we rely on advanced tools to uncover more and more celestial wonders. But no matter how powerful our equipment becomes, there's a hard truth. We'll never directly see what lies beyond the cosmic horizon. Or will we? What if I told you there's a way to work around this limitation? Though we can't view stars 100 billion light-years away, the universe itself gives us clues, one of which is the extraordinary neutrino. Neutrinos are almost unimaginably tiny particles. With a mass so close to zero, they're often called ghost particles. But their near invisibility makes them special. Unlike light or other particles, neutrinos interact so weakly with matter that they can travel across the universe virtually unimpeded, at speeds nearing that of light. Born from cosmic events like nuclear reactions in stars or explosive supernovae, neutrinos carry the story of their origins across billions of light-years, all the way to Earth. Over their journey, They can even transform into particles with lower energy, adapting as they traverse the vast distances of space. Detecting these elusive messengers has been a monumental challenge for scientists. Their tendency to slip through matter undetected makes capturing them almost like trying to catch shadows. Yet, with ultra-sensitive detectors being developed, we're on the verge of a breakthrough. One day, neutrinos may unlock the secrets of what lies beyond our cosmic horizon, giving us a glimpse into regions of the universe we can't otherwise explore. But neutrinos aren't the only tool for peering into the unseen. Enter gravitational waves, ripples in space-time caused by some of the most dramatic events in the cosmos. When massive objects like black holes collide, neutron stars spin, or binary stars orbit each other, they release these waves, which travel outward at the speed of light. By the time they reach Earth, gravitational waves are no longer powerful enough to cause destruction, but their faint echoes carry invaluable information. In 2016, scientists at MIT used gravitational waves to detect the merger of two black holes 1.3 billion light-years away. This milestone marked the beginning of a new era in astronomy. Like neutrinos, gravitational waves are messengers from the cosmos, helping us study events far beyond our direct observational reach. With advancing technology, they'll play a critical role in unveiling the mysteries of the universe's hidden corners. Despite these advances, we face an unavoidable hurdle: the relentless expansion of the universe. After the Big Bang, space didn't just expand, it kept growing. Though the rate of expansion slowed for a time, dark energy is now accelerating it again. This means galaxies and other celestial objects are drifting farther apart. Every 3.26 million light-years, this expansion speeds up, creating vast distances that light, and even gravitational waves, struggle to cross. As the universe grows, so does the particle horizon, the boundary of what we can observe. New objects once beyond this limit gradually appear on our star maps, as light from their distant past finally reaches us. However, many objects will forever remain out of reach, racing away so quickly that their light can never bridge the gap. This creates another barrier: the event horizon. This limit, currently at 16 billion light-years, defines the farthest distance from which any signal, light, neutrinos, or waves, can ever reach us. Galaxies beyond the event horizon might as well be in another universe. Any signals they emit will stretch into undetectable frequencies as the expansion carries them farther away. In time, even nearby galaxies could slip past the event horizon, isolating us further. The same expansion also shapes the Hubble horizon, a theoretical boundary about 14.5 billion light-years from us, beyond which objects move away faster than light itself. Though light from beyond this limit may eventually reach us, as the Hubble horizon expands, in the far future, it will shrink again, cutting us off from the greater cosmos. Imagine this distant reality. Billions of years from now, the Hubble and event horizons will merge, forming a new boundary with a radius of 63 billion light-years. Beyond this point, no light, no waves, no signals of any kind will ever reach us again. Humanity, or whatever life exists, will be confined to a cosmic bubble, surrounded by an impenetrable veil. Even within this bubble, the stars and galaxies we see today will dim and disappear, as the universe's relentless expansion pushes them farther into the void. While this might sound bleak, it's not the end of the story. Neutrinos, gravitational waves, and advanced technology hold the promise of uncovering more of the universe's secrets than ever before. Someday, we may even establish new particle horizons on other planets, stretching the reach of our observations. While we may never escape these cosmic limitations entirely, we can learn to adapt and push their boundaries. The universe challenges us with its vastness, but it also rewards our curiosity. For every horizon we encounter, there's another to reach beyond it. And though our current bubble of knowledge feels small against the infinite backdrop of space, the journey to expand it is a testament to humanity's unyielding desire to explore, discover, and understand. One day, we may cross our own horizons, stepping into a cosmos of limitless potential and new frontiers. All that remains is to wait. For as long as we've existed, humanity has looked to the stars, captivated by the endless expanse of the universe. We've traced constellations, counted stars, and imagined what lies beyond our small corner of existence. But how often have we truly pondered the ultimate end? Not just the end of humanity, but the end of the universe itself. What might the final moments look like? Will it be a cataclysmic blaze of glory? Or will the cosmos fade into an unexpected, eternal silence? Curiosity is the force that has always driven us forward. It pushes us to explore the unknown, to question the infinite, and to seek answers beyond the boundaries of our understanding. Today, we embark on an unprecedented journey, not across space, but through time itself. Like grains of sand slipping through an hourglass, each passing moment brings us closer to the universe's ultimate fate. The question isn't just when this will happen, but how. And what will it mean for us, the fragile inhabitants of a small planet, in the face of such vast cosmic scales? We begin our journey in the present, the Anthropocene, the age of humanity. This is an era defined by our profound impact on Earth. Over millennia, we have reshaped our planet, leaving an undeniable imprint. From the early days of hunting and gathering to the rise of advanced civilizations, humanity's influence has touched every corner of the globe. But our rapid progress has come at a steep cost. The Earth, which once nurtured us with the stable climate of the Holocene, now struggles under the weight of human activity. Our relentless consumption of resources and ceaseless expansion have set dramatic changes in motion. Climate patterns are shifting, ecosystems are collapsing, and the delicate balance that sustained life for thousands of years is unraveling. The question looms: what kind of world will we leave behind? As we move forward in time, the transformations to Earth and beyond become strikingly clear. By the year 2500, Earth's magnetic poles may flip, an event that will disrupt technologies and force humanity to adapt like never before. In 4,385,000, the return of Comet Hale-Bopp lights up the night sky, a breathtaking reminder of the cosmic cycles that continue regardless of human existence. By the year 5000, the polar ice caps have melted entirely, submerging coastal cities and leaving behind ghostly relics of civilizations that once thrived. Humanity's footprint on the planet is undeniable, as rising seas reshape the world. Fast forward to the year 6000, and we face an existential crisis. A massive asteroid hurtles toward Earth, its collision altering life as we know it in a catastrophic event. In 8000, a distant star explodes in a spectacular supernova, its dazzling light outshining entire galaxies. It's a vivid reminder of the ever-changing universe where stars are born, live, and die in a cosmic ballet. 1 billion years from now, the Sun, our life-giving star, will begin to scorch the Earth. Its brightness increases by 10%, halting photosynthesis and withering the planet's vegetation. By 1.3 billion years, the oceans have evaporated, leaving behind a dry, desolate husk, a far cry from the vibrant, blue-green world we once knew. By 7.5 billion years, the Sun expands into a red giant, swallowing Earth entirely and reducing our home to cosmic dust. The story doesn't end there. By 10 billion years, the Sun becomes a white dwarf, a faint, cooling remnant of its former self. The universe continues its slow march forward. By 100 trillion years, the stars, once the brilliant beacons of the cosmos, begin to wink out one by one, plunging the universe into an era of chilling darkness. In the age of degeneration, trillions of years from now, the remnants of stars, white dwarfs, cool and fade into black dwarfs, dead stars invisible to the eye. Gravity continues to reshape the cosmos, flinging stars and planets into the void, occasionally sparking the birth of new stars in fleeting moments of light. But even this brief glimmer of hope fades. As time stretches on, the fundamental building blocks of matter, protons, begin to decay. Atoms disintegrate, leaving behind only ghostly neutrinos and photons. The universe erases the last remnants of its physical history, leaving a cold, empty expanse dominated by black holes and scattered particles of light. By 10 quadrillion years, the universe is a shadow of its former self. Black dwarfs and black holes are all that remain, drifting in an endless void. The relentless expansion of space-time continues, stretching the cosmos into an incomprehensible emptiness. Matter as we know it ceases to exist, and the universe enters a cosmic winter, a cold, silent echo of its fiery birth. And yet, even in its quiet demise, the universe tells a story of light and darkness, of creation and destruction. Though its final moments are shrouded in silence, the legacy of the cosmos endures, a haunting reminder of the cycles that define existence. For all its vastness, the universe remains a testament to the beauty and fragility of time itself. The universe, as we know it, enters a hauntingly quiet chapter, the era of black holes. Gone are the black dwarfs and the last glowing remnants of stars, their mass surrendered to the endless pull of the expanding cosmos. What remains are black holes, the ultimate survivors of the cosmic timeline, scattered like silent sentinels across the vast emptiness of space. Among these, supermassive black holes reign supreme. Born from the explosive deaths of massive stars and the mergers of smaller black holes, these celestial giants have grown to incomprehensible sizes, devouring matter and energy on a scale that defies imagination. Their powerful presence sends ripples through space-time in the form of gravitational waves, faint echoes of the universe's once vibrant life. These waves are the final whispers of the cosmos, like the fading toll of a bell at the end of time. But even black holes, seemingly eternal, are not immune to the laws of physics. In the 1970s, physicist Stephen Hawking proposed a revolutionary idea: Hawking radiation. According to quantum physics, particle-antiparticle pairs form near a black hole's event horizon. One particle escapes into space, while the other is consumed by the black hole, leading to a gradual loss of energy and mass. Over unimaginable timescales, this process causes black holes to shrink and eventually vanish entirely. The death of a black hole is the universe's final act, leaving behind nothing but an endless, silent void. Since the Big Bang, the universe has expanded relentlessly, driven by the mysterious force of dark energy. This enigmatic energy acts as the opposite of gravity, accelerating the expansion of the cosmos. Meanwhile, dark matter, the invisible scaffolding of the universe, exerts a counterbalancing gravitational pull. While dark energy currently dominates, the future may hold a dramatic twist in this cosmic tug-of-war. Some theories suggest that as the universe continues to expand, the influence of dark matter could grow stronger. If its gravitational pull eventually overpowers dark energy, the expansion could slow, halt, and even reverse. This scenario, known as the Great Contraction, envisions the universe collapsing inward, like a cosmic rubber band snapping back. Matter and energy would compress into a singularity, a point of infinite density and temperature, where the laws of physics as we know them cease to exist. And yet, even this catastrophic collapse may not be the end. Out of the singularity, a new Big Bang could erupt, sparking the birth of an entirely new universe. In this way, the cosmos might follow an eternal cycle of creation, destruction, and rebirth, a rhythm of beginnings and endings that transcends time itself. As we reflect on this cosmic journey, we are reminded of our own fleeting place in the grand narrative of the universe. Our existence is but a blink in the vast ocean of time. Yet, within this brief moment, we have the privilege to marvel at the cosmos, to question its mysteries, and to wonder about its infinite possibilities. Perhaps the greatest revelation lies in this. In a universe defined by cycles, the end may not be an end at all. Instead, it could be the start of something entirely new, a testament to the endless potential of existence, forever unfolding and forever unknown.